Hello, my name is David Eastwood with Geotech Engineering and Testing. We're going to be talking about geotechnical, environmental, and geoforensic seminar for residential foundations. Today, sponsored by Greater Houston Builders Association. Some of the stuff that I'll be talking about today, you can go to the website, geotecheng.com, publications, guidelines, and get some of that stuff. If you need to reach me, my email is de@geotecheng.com. My phone number is 713-699-4000. We have a lot of builders today that are listening, and also we have a lot of structural engineers. So that's why we have a lot of builders and structural engineers and some civil engineers. A little bit about our company. Geotech Engineering and Testing has been around for about 35 years. We're located in Houston. We work all over Texas, Louisiana, New Mexico, and Oklahoma. We do geotechnical, environmental materials, and geoforensic engineering. We have a staff of about 60 engineers, geologists, technicians, and support staff. And we have our own drill rigs. So that's why builders like to use us, because we get out there and get the work done quickly. We're out there the next day. We got, 7 rigs, so we can get on the stuff quickly. If you have questions, please type them in. And, there's a Q&A button at the bottom of your screen. You can see the questions, but go ahead and type the questions in, and that way I can answer them as I go through. We're going to be talking about the residential foundations. Some builders send me some pictures of some of these houses in weird places. If you look at this, I don't know, it's a lot of work to do this. Some weird looking houses out there in the world. In South America here. Look at this one here. That's how you go up. Tree house, ocean house. That's an old Telfair before it got filled up. When you do a development, of course, you go out there first, clear the trees and stuff like that, and do grubbing and get all the roots out. Cut your streets in, put your streets in, and put in your utilities, and then you put your detention pond, and then you have a subdivision. It's a pretty complicated basically work. There's a lot of work involved to develop a subdivision. And so there's a lot of expertise and a lot of disciplines that are involved in development of a subdivision. So when you develop a piece of land out there, you may have a bunch of trees, or you could be just bare ground. One of the things is you have to do before you develop anything, you got to do a phase 1 environmental site assessment. We do the environmental site assessment in accordance to ASTM 1527-13. And, you go out there and try to develop a piece of property, and there's a service station not too far away. It's an old service station. It's got underground storage tanks. Some of these tanks leak. And when they get into the soil and groundwater system, can travel all over the place and contaminate your site. So if your site is contaminated, you're responsible for the cleanup costs, even if somebody else caused it. If you have a bunch of drums on the site, it can cause carcinogens and chemicals in the soil. All that is an issue. Let's see, we can move this down here. Pipelines, some of these pipelines can leak. And so if you have an oil pipeline can leak out there and contaminate your subdivision, that's a big problem there. If you're out there in Leak City and you got all these tanks out there, and these oil tanks could be leaking and contaminated this site here, you're responsible for the cleanup costs. If you're out there doing stuff out there, you got a landfill, it's a sanitary landfill. As if this thing has got leachates, basically when it rains, water hits all this waste, goes into the soil and groundwater. It's called leachates. And if they're contaminated, you're responsible for all the cleanup costs. A lot of builders are going out there in the parts of Houston, Midtown area, for example, tear down old buildings and build new subdivisions and new condos. Well, some of these structures, you know, they have lead-based paint. They got asbestos. So if they were built before 1978 or so, you're gonna have to check for asbestos and lead-based paint. Cemeteries, you stay away from them. You cannot tear them down. If you're near close to cleaners, some of these cleaners, they got on-site cleaning where they got tanks, and these tanks got chemicals in them that are cancer-causing carcinogens. These solvents can go into the soil and groundwater system and contaminate the whole area. And as they do that, again, if they hit your property, you're responsible for the cleanup costs. So you got to make sure if you got a cleaners that's not contaminating your site. So TCEQ, Texas Commission on Environmental Quality, has got pretty strict rules with respect to the cleaners. So as one of the things you do is before you develop a piece of property, you can look at the aerial photos. You know, for example, in this specific property in 1938, that's what it looked like in Pasadena. And then in 1944, they got some subdivisions going in there. And nowadays, in 1989, you have service station here, car wash here, cleaners here, service station here, chemical plant here. So, and you got another service station here. So all these guys can cause contamination to this site. So you do a risk-based analysis, which is a phase 1 environmental site assessment, to see if you got any contamination to the site as a result of these facilities. This is a project out there in the Heights area. This is North Main. This track here, when we look at it in 1925, that's what it looked like. There was one house on it. In 1969, there was a gas station right there. That gas station was all contaminated. We went in there and checked it out, and they were going to go build a bunch of houses here. And so we had to dig out all that contaminated soils and take it off site. And so that's very important. So when you do a phase 1 site assessment, if this is your property, you go 1 mile on each side of the property and check for contamination. And these are all the stuff that you got around it. These red, dots in here, it can cause contamination to this site. There could be leaky underground storage tanks. There could be oil wells. Here's a site over here. The red spots are all the oil wells. That means it's oil wells, they got oil pits. And when you got oil pits, they can cause contamination. And, you get a map like this. On this side, you got about 14 leaky underground storage tanks within 1 mile of the site. One of them is within 1/8 of a site. The other one is within 1/8 to 1/4 of a mile. 2 of them is within 1/4 of a mile to 1/2 a mile. 10 of them is within 1/2 a mile. So, again, we'll look at the risk of these things like underground storage tanks, leaky underground storage tanks, on all the other things that EPA has. So to do a phase 1 environmental site assessment, we get out there, do a site visit. We check with the regulatory agencies like TCEQ, EPA, Texas Railroad Commissions. We'll look at the historical use of sites. We do interviews. Sometimes we do property title review, see who owned the property. If the property was owned by an old company, then there's a chance that there may be some oil wells there. So if there's existing structures there, we check for asbestos and lead-based paint. And so that's pretty involved. And if there's a risk of contamination, we get into phase 2 environmental site assessment. That one is that phase 2 environmental site assessment is done in accordance to ASTM 1903. It's like you go to the site, you're going to start excavating, you're going to see all this free product here, the oil out there in the ground. And so all these chemicals that are leaching into the soil and groundwater system, start excavating and you're going to see this stuff, they can cause contamination. So here's a leaky pipeline here, kind of contaminating the site here. Pipeline rupture here. Damage to the wildlife, oil wells. This is in Cypress Wood area out there. We're clearing for the roadways on the subdivision, and we found this wellhead that was not in anybody's database. So we had to go back and check it to make sure this thing is not leaking and there's not a problem. And so if there's any contamination on the site, we get into remediation or phase 3. We start digging out the contaminated soil and groundwater, dump it out here on the side, cover it with plastic, put it in containers like this, and take it to a chemical dump site that's designated as an industrial use. And then we'll backfill the holes with select fill, compact 95% of standard Proctor density and lifts. Make sure you can put a structure on it. Wetlands. Wetlands is a big deal when you do a land development. Wetlands are areas that are inundated or saturated by surface or groundwater at a frequency and duration sufficient to support and, under normal circumstances, to support a prevalence of vegetation typically adapted for life in saturated soil conditions. Wetlands include swamps, marshes, bogs, and similar areas, as identified by the U.S. Corps of Engineers and by the EPA. These are typical wetland pictures. A lot of them in Galveston County, Harris County, Montgomery County, Fort Wayne County, Brazoria County. The water came all the way up here. There's a lot of them in Galveston County. This is in League City. We're out here building this subdivision here, but there was a bunch of wetland here. We left it alone. We didn't do anything with the wetland. These are some pictures of the wetland on top of vegetation that grows in it. You can see this area has been inundated with water up to here for a long time. How do I know I have jurisdictional waters? You can do what's called jurisdictional delineation that are performed on a property based on waters of the United States and Clean Water Act 404. Most often the preliminary jurisdictional delineation is done and you give it to Corps of Engineers. The applicant can decide whether or not they would like to final approval of the delineation or they would like to proceed with the application and with only a verified preliminary delineation. Wetland delineation are conducted in accordance to 1987 U.S. Army Corps of Engineers Wetland Design Manual. To have a wetland, you should have water, hydric soils. These are black, smelly soils that have been underwater for a long time. And you have certain plants that grow under basically saturated condition. So hydric soils, water-loving vegetation, and wetland hydrology, which is saturation for 7 days during the growing season. You should have all these 3 components to have wetlands. We don't do wetland studies, but I just want to give you some idea what wetlands are. Subsidence. We've got problems with subsidence in Harris County, Montgomery County, Fort Wayne County, Brazoria County. Subsidence is a lowering of the elevation of the land over the surface over time. So what happens is in the Houston area, if this is Katy and this is Galveston, this is our gumbo, clay, Beaumont, and then below that we got these sandy soils called Chicote Aquifer. And this Chicote Aquifer, it's got water in it, and you go down about 1,000 feet or so, and people drill holes to get water, or they go all the way down to Jasper, 4,000 or 5,000 feet, and to get water. These are aquifers, these bodies of sand that are full of water. Okay, here's another picture of it here. This is a Chicote Aquifer, goes all the way to Frio. Aquifer goes 7,000 feet deep. Okay, this is all the way in Humble area, Montgomery County. And so, this is Humble. So this is all bodies of sand. We got a lot of sand out here. So when you take that water out, the ground starts dropping. Okay, this is Goose Creek oil field here. It used to be above the ground, but it dropped 3 feet due to subsidence. It's covered with water now. So areas that basically are subsiding are really prone to flooding. This is a wellhead out there. Initially, when it started, it was right here, but in 2004, it's in Baytown. That's the space. The ground dropped underneath it. This is the Kingwood area that's kind of flooding. This is Brownwood subdivision in Baytown. That's what it looked like in 1944, 1953, 1978, 1989, 202, 2012. So it's going underwater. It's just subsiding. Again, part of the areas that are subsiding, they got flooding problems. This is land subsidence between 1906 and 1987. 9 feet of subsidence in the Baytown Deer Park area and the ship channel. And you can see out here where GHBA is. There's been as much as 5 foot of subsidence. This is the basically 2018 University of Houston subsidence map that shows Montgomery County is dropping at a rate of 1 to 2 centimeters, like half an inch to an inch a year due to subsidence. Okay. So this is the predicted subsidence between 1995 and 2030. And you can see the Houston area is going to drop as much as 5 feet in some areas. Luckily, we're not going to use groundwater as much with our North Harris County Water Authority, West Houston Water Authority, North Fort Bend Water Authority, San Jacinto River Water Authority. So all these guys are going to a surface water system, so we're not going to have as much subsidence. Addicts area has been dropping almost half an inch a year due to subsidence. That's the number of years and the ground dropping. Pasadena is leveling off. From what I understand, they're not using groundwater as much anymore. Faulting. So if you got part of Houston that you're taking all this groundwater out or oil out, that areas are dropping and subsiding. And there are areas that are not doing, we don't have as much wells in, so they're not dropping. So there are cracks that have been in the ground millions of years. These cracks become activated and they start showing up near the surface. Sometimes they don't show up so near the surface, they're just below the surface. These cracks can extend 200-300 feet deep. They're called faults. There are about 300 faults in the Houston area, all the way from Corpus Christi to Beaumont. They move at a rate of half an inch a year. Sometimes they don't move at all. There are some that become stagnant and then they start moving again. Here's a fault lineation going through this house out there in the Spring Branch area. This is a portion of the fault that's up. This is a down portion of the fault. Again, fault going this way. This is a house on a fault. This is the woodland area. And you can see over here, the fault's going towards this house. That's a part of Hockley fault system that crosses the woodlands as well. Here's a fault lineation going through this parking lot, cracking it, going towards this structure here. Post Oak area. Post Oak area. Fault's got 2 components, the up-thrown section, the down-thrown section. This is the area that's dropping. So as it drops, you got the crack over here. These are soil layers. They get out of whack. So you can go back, you can do resistivity and SP potential. Basically, these are tests that you can do and to determine if there's a fault there. So it's a part of a phase 2 or phase 3 fault study. And so you do geophysical testing to see if there's a fault there. So that's the fault scarp. This is the down-thrown, this is the up-thrown section of the fault. You see the fault going this way from aerial photos. This is the down-thrown, this is the up-thrown. We do a lot of phase 1 fault studies for the builders and developers. And, you know, we determine if there's a fault there. Here's the lineation, down-thrown section, the up-thrown. The down-thrown is usually darker in color when you look at aerial photos because there's more moisture out there. Water stands over there. It's the down-thrown section, the up-thrown section. It's hard to tell if there's a fault there if the site is wooded or if it's got tall grass. So we have to go out there, use what's called LiDAR. LiDAR uses laser light to measure distances. And so we use LiDAR, basically it's from airplane, sending these LiDAR rays that basically hits the ground, comes back, it tells you the elevations. And so you can see if there's a lineation or change in elevation here. You can see that over here on the LiDAR, the fault right there. So that's a long point fault, and this is the site. So here are the faults out here in Texas, and you can see all the way to Dallas. We got faults out there in San Antonio, Austin. Of course, most of the faults that are active are in the Gulf Coast. There's about 300 of them near Houston area and Beaumont. And you can see some fault maps in here, and you can see the Hockley fault map goes to the Woodlands area here. These fault maps are on our website. You can see them. These tickers here are basically down-thrown section of the fault. That's the up-thrown section of fault. It's basically a Long Point fault, Piney Point fault, Eureka Heights fault. This is a track out there in Pearland. These guys wanted to develop this 72-acre track out there in Pearland. It was near a salt dome called Macoa Salt Dome. There are a lot of faults there in Pearland. If this is the track, this is the faults going that way towards it. So the fault's crossing the property here. Where the fault crosses the property, we basically call it a hazard zone. It's about 130 foot wide and is twice in size in the down-thrown section of the fault that's up-thrown section of the fault, because down-thrown section of the fault is more active. So you can't build any structures here. You can have roads crossing it, but you cannot build houses. You can make it a detention pond, linear detention. You can make it a playground, but don't put structures there. This is a building that's going next to the fault out there in Pearland. It's a Pearland Parkway. They were going to build this Montessori school here. We told them not to build it next to the fault, but they did. They put it on piers. These are deep piers, about 20, 25 foot deep. And this is the beam that underneath the building. These are the anchor bolts to adjust it. So every year or two, you got to go back and adjust this building because it moves due to the faulting. Field exploration. So if you guys call us for a soil test, this is our building here, and this is our rigs. Like I said, we have about 7 rigs. These are portable rigs. These are the big rigs. These are medium rigs right here, go 20 feet deep. These guys go 120, 150, 200 foot deep in this one here. So if your site looks like this, nice and dry, we can use our basically truck mounted rig out there. This is a medium rig. We can get out to do the borings. If you got to go do deeper borings like a lift station, we got to use our bigger rig. If your site is wet and you cannot drive on it with a regular truck, you got to use a buggy rig. These buggy rigs, they got big tires, and they can go to the wet places the regular rigs get stuck at. This is Fort Wayne County out there on 1743, I guess is what's called, where Safari Club is. One of the subdivisions, we had to do borings out there in the water. This is woodlands. For you to do borings in the woodlands, you need to do a clear path. So you get a dozer to clear a path so they can get to the boring location. We do our borings next to the biggest tree on the property. Trees tell us a lot about the foundation system, the depth of active zone on the specific sites, how deep the root fibers extend. Give me a second here. I'm kind of hot in here, so I'm going to take my shirt off. It's kind of hot in here, so I'm going to take the shirt off. You make it a little cooler. Sorry there. Okay. A little cooler here now. So we have all these trees in here. We got to do the boring right next to them. We pick up root fibers from this drilling next to the trees, and they tell us the depth of active zone. Go out there. So when we go on a job site, we do the boring right next to the biggest trees on the site, because they tell us about where the foundation needs to go. Because by knowing the depth of active zone, we know where your building needs to go, the foundation. We drill with a portable rig. This rig here, you drill a hole with it, and you get a sample with driving this on top of the rod and pushing it into the ground. You push the rod in the ground, and you get a soil sample. Here's a portable rig, goes up to about 25 foot deep. On subdivisions, sometimes you go out there, especially in the springtime and fall, we get a lot of rain. All these pads are wet, so we use our ATV, pull the rig out there with it, and we do our borings. And we get our samples with what's called a Shelby tube sampler. These are 3-inch diameter hollow tubes that you push it hydraulic into the soil. These are hollow, and you get a soil sample that looks like this. We're going to put a soil sample in here. You cut the ends of it, put it in foil. You give it a job number, boring number, and then put it in a wax box. You take it to the lab. And these are the root fibers. Root fibers tell us with the depth of active zone. In general, roots from trees extend to the areas where there is oxygen and water. When there's no oxygen or water per se, the roots stop. And that's the depth of active zone, okay? Again, you see the root fiber. In areas where soils are sandy, we cannot get a Shelby tube sample. So we drive a sampler into the ground with dropping 140-pound hammer, 30 inches. It's a 140-pound hammer. You drive it 30 inches and then drive it into the ground 18 inches. 6-inch, 6-inch, 6-inch. It's a split spoon sampler when you get sandy soils. Here's the sandy soil. So if you drive this stuff into the ground and you get a blow counts between 0 to 4 per foot, you got very loose soils. Like if you're out there in the Woodlands area or Bridgeland, you got loose sands out there. 5 to 10 is loose. Medium dense, 11 to 30. Dense is 31 to 50 blows per foot. If you start going deeper, you're going to hit rock. But rock in Houston is about 2,500 to 5,000 feet deep. Now, we have some cemented sand out there near the surface within 30, 40 feet. But the real rock, you know, like limestone or stuff like that is deep in the Houston area. That's what the rock core looks like. Groundwater. This is the groundwater. Typically, groundwater changes anywhere from 10 to 30 feet in Houston area. You they get a tape measure with a weight at the end of it. You throw it in a hole. When it hits the water, it goes plumb, and then you know you hit the water. That's how you measure the water level. We have another water table in Houston called perch water table, where you have sandy soils and over clay. When it rains or bad drainage, water comes in and sits on top of the clay in the sand and saturates that sand. It's called perch. So if you want to go out and build a house out there, the ground starts pumping and water just stands on top of the clay. You can't go anywhere. So that's called perched water table. Just basically water just sits and you see it, you dig a hole, it gets filled up with water. Number of borings. So if you want to build a custom home out there, if the house is less than 3,000 square foot, when you tear it down, you get something like we do a couple of borings, 20 feet. That gives you peer recommendations as well as slab on grade. It's a typical West U lot here, 50 by 100. It's better just do the borings when the house is still there. You can do it next to the biggest trees, B1 and B2. We'll also do a lot of development projects. We do preliminary before somebody buys the land. Right now, we got a 1,200 acre tract out there in Fulshire somebody's buying. And we're doing like 120 borings, essentially one boring every 10 acres. We go out there and do scatter borings every 10 acres throughout the site before they buy the property, because you got to know what kind of soils you have before you buy the property to develop, because it can be very expensive to develop if you don't know the soils. You got to do an environmental site assessment, you got to do a fault study, and you got to know what kind of soils you got when you buy a piece of property to make sure you have lower your risk and make sure you don't have that much risk when you buy the property. You do one boring every 10 acres for a preliminary study. Lot borings, after you developed your lots and stuff, you cut your streets in, we go out there and do the borings on the lots. Usually we got multiple builders in there. You got the blue, one builder, the red or brown is another builder. And so we go do the boring for the whole subdivision and save money for both builders. That way they don't have to do as many borings. We do one boring every 4 lots or every 200 feet spacing. Now, that's the minimum. Most builders are doing every other lot borings nowadays. So we do every other lot for them because soils vary. Soils are very heterogeneous in the Houston area. So one lot you PI 50, the other lot maybe PI 30. So your slab may be different. So these are the borings that you do out there for the subdivision. These are the one builder's lots, you know, the blue lots. So we're doing it for one builder here. So you do one boring every 200 feet or one boring every 100 foot, or we have clients who do boring every lot. In the areas that lots that are wooded like Kingwood, you back up to the lot, to edge of the trees, and as close as you can and do the boring. Laboratory testing. Let's talk about laboratory testing a little bit. This is the testing that we do in the labs called Atterberg limit test. In this test, we want to know how much water we should add to the soil for it to behave liquid. So we take soil sample, you put it in this cup, add water to it, and make it liquid. You get some sample of that, you put it in this cup, and turn the handle 20 to 30 times, and you get a sample of it here. You cut a groove in here. You turn the handle. When the groove comes together, you take a sample of it. You put it in a cup like this, and you get the wet weight of it. Then you put the oven and you dry it up. And then you get the dry weight of it. The difference between the wet weight and dry weight is how much water is in that soil. So that's how much water is in the soil for it to behave liquid. The other test we do in the lab is called plastic limit test. In this test, we're trying to find out how much water we should add to the soil for it to behave semi-plastic. We roll the soil to 1/8 of an inch. We put it out there on scale and get the wet weight of it. Then you put it in the oven and dry it up and get the dry weight of it. We will know how much water is in the soil for it to behave semi-plastic. The difference between liquid and plastic limit is called plasticity index. So if your soil has got a liquid limit of 50, like 50 moisture when it's wet, and 30 when he's plastic limit, the PI is 20. If your PI is 20, it's got low swell potential. If it's between 20 and 30, it's got moderately expansive. The PI between 30 and 40 is highly expansive. As above 40, it's very highly expansive. A couple of tests we do in the laboratory. It's a hand penetrometer and a torr vane test. In a hand penetrometer test, we take a sample and push this hand penetrometer into it. You can read here what kind of a strength it has. In a torr vane, you put it on the sample, you shear it in torsion, rotate it, and you can read here what kind of a strength it has. That's unconfined compression test. You put a soil sample in a machine like this and crush it and see what kind of a strength it has. You just crush it in hand. You can use that for your bearing capacity for drill piers and your grade beams for your foundations for your slab. Soil types. We have all kinds of soils in Houston, pretty variable. Gumbo clay, that's a clay site. Sand, that's a sandy site out there near the beach in Galveston. You know, here's a sandy site. Silt. Silt grain size is bigger than clay, but smaller than sand. Really a bad material to build on. This is a silt site here. You can get stuck in it dry. It's really cohesionless soil. It doesn't have any cohesion. It doesn't stick together. So we have clay. You go deeper, you got orange clay. You go deeper, you got white clay. You go deeper, you get into weathered rock. That's a clay, gets weathered rock, and then you get rock. Like I said, rock in Houston is about 2,500 to 5,000 feet deep. Fill. We build subdivision all day on top of fill. So what we do is, when you do mass grading out there, you put fill on these lots. So essentially, as long as the soil is compacted to 95% standard Proctor density and is free of organics, you can use it as fill. Engineering analysis. These are where the expansive soils are in Texas and Louisiana. Soils in Texas are pretty variable. So you're going to need a soil test when you do subdivision development, or if you do a custom home building. In the US, these are the soils that expand up to 1,500%. This is by US Corps of Engineers. Expansive soils. Expansive soils. Again, Houston, Dallas, San Antonio, and Austin, they're all located in the geology of an area that's got expansive soils in it. So if you go through Houston, we got Kingwood, Roman Forest is kind of where I live. You got sandy clay, good soil here. You go to Kingwood, everything goes bad. You got gumbo clays with trees. You go to Tascasita, you got sandy soils on top of gumbo clay with trees, which is the worst combination you can have. Channel View, Galena Park, Pasadena, South Houston, Missouri City, Friendswood, League City, Dickinson, they all have a bunch of gumbo clay. Sugarland, your territory, Rosenberg, you go out here, all these areas, Fulshire, you got highly expansive soils out there. Watch out for the soils in Fulshire. They're tricky. They got expansive soils and can cause problems. Cinco Ranch, sandy clay, good soils, perch water table conditions. Bridgeland, you got sandy clay, sand, perch water conditions. Same with Fairfield and the Woodlands. Tomball has got all kinds of soils. Some areas are expansive, some areas are real sandy. So just variable. You go inner city type stuff, Bel Air, West U, Tanglewood, you got highly expansive soils, lots of trees and attorneys. So watch out if you're building in West U, Tanglewood, Bel Air areas. One of the concepts that you need to worry about is called potential vertical rise. Potential vertical rise, or PVR, is how much a site heaves up due to expansive soils. So here's a PVR map of the Houston area. So if you're here in Bel Air, West U, you got a PVR about 4 or 5 inches. That means the ground can move up to about 4 or 5 inches. If you're in Bridgeland, it's about 1.5 inches. Brookshire, about 1.5 inches. You know, you go Spring, Tomball, Spring's 1.5, Tomball 1 to 4 inches, the Woodlands 1 to 4 inches. Patton Village 1.5 inches, Kingwood 3 to 4 inches. Baytown about 5 inches, Pasadena 5-6 inches, Friendswood 5-6 inches, Pearland 5 to 6 inches, Greatwood 6 inches. So it just depends where you are in Houston. You're going to have a lot of movement. And usually the more movement you're going to have, the more expensive your foundation is going to be. So this kind of gives you an idea how expensive your foundation is going to be if you build in different parts of Houston. For typically, we like to keep the PVR to less than 1 inch. Now, when you doing a post-tension slab, we can typically build out there on houses out with PVRs up to about 4.5 inches. I mean, but if you got trees out there, that's a different story. If you got trees and highly expansive soils, then you may have to do chemical injection to get the PVR down. One way you can reduce the PVR is by make sure you stop having drastic changes in moisture. Put sprinkler system all around the whole house. That way everything stays wet all the time. Extend your exterior beam down. The deeper your grade beams go, the less movement you're going to have. There's less moisture change under the slab. When you put driveways in, put space between the driveway and the house. Don't attach it to the exterior beam, because what's going to happen is this provides what's called a horizontal moisture barrier, and this area doesn't move, but this area here will move because this area is planter. You got planter areas with sprinkler system, so the house will move up and down in the front, and it doesn't move back here. So you develop cracking. So you want to put a space between the driveway and the house. Provide a slope of about 5% in the grass away from a house. If you cannot have slope, put area drains. Don't use sand in your slab areas, especially in the areas where you got expansive soils. If you are building in Bridgeland or in Cinco Ranch, it's okay to use sand. You develop what's called perch water table, but it's not going to cause major problems. But if you got gumbo clays, if you're building in Rosenberg, you're building out there in areas with highly expansive soils, do not use sand. Pasadena, LaPorte, all those areas. You can reduce the movement by removing the expansive soils and put select fill there. So if you got a site with a PI of 60, active zone of 10 feet, you got to take out 7 feet to get your movement to 1 inch, which is not economical. Nobody does that. You just go with what's called a structural slab on pier here. Some areas, when you got a drought situation, you got shrinkage cracks in your soil. These are called slick sides. Okay, these are 45-degree angle cracks in the ground. So what happens when you develop these cracks, they get filled up with soil and dirt with time blown in there. So you get a big rainfall, the area soil wants to swell. It doesn't have any place to go because it's already filled up. So it cracks the soil. It's called slick sides. All right, pretty slick at 45-degree angle. So when we look at Houston geology, north of Buffalo Bayou, you got sandy soils. South of Buffalo Bayou, you got Beaumont Formation, which is very highly expansive soils. So over here, you know, the Woodlands areas and the Bridgeland area, you got sandy soils. Here where the Rosenberg is and the Fulshires, you got Beaumont Formation gumbo clays. This is a typical boring log, where here, this is the depth, this is the soil type, and here are the properties. The strength, the PI. From 0 to 2 feet, you got clay. From 2 to about 14 feet, you got clay. Then you got sand. When you drill, you hit the water at the sand level. Then hydrostatic pressure pushes it up to about 9 feet. So water table changes, but actual water table is really at 13 feet. This soil has got a PI of 38, 39, and 35, and a strength of about 1,000, 1,500 PSF. So if you're building a subdivision along the street, you got clay layer, the first layer, from a depth of from 0 to about 12 feet. Then you got sand, then you got clay. So if you're going to go put your storm sewer in or sanitary line, when you go through the sand, you may have to do sheeting. And of course, you may have to do dewatering. Or if you're going to use foundations, you want to put your piers below the sand or above the sand, depending if the soils are expansive. The type of foundation we use in the Houston area are drill piers, piling, auger cast in place piles, helical pile, press piling, conventional reinforced slab, post tension slab, spread footings, mats. So a typical custom home, if you are building in Westview, Bel Air, you're going with a structural slab with piers. That's the lowest risk foundation. As a builder, you need to talk to your structural engineer and homeowner about the risks of different foundations. If they don't want to have any movement, they got to use a structural slab with piers. Most expensive foundation. Then you can go slab on fill supported on piers. You calculate the amount of fill you need based on the PVR. So to keep the PVR to less than 1 inch, you may need about 6 foot of fill in the piers. Floating stiffened slab on top of piers. You put the piers in and you put a floating slab on top of it. The slab can go up, but it cannot go down because of piers. The next one is a super slab system. And that is just a waffle slab that goes into the natural soil, does not require compaction underneath it because all the grade beams go into the natural soils. The slab spans in between the grade beams. It's about 6-inch thick slab. Some builders like to use it. Next one, of course, is post-tension slab, which is about 95% of the slabs in Houston are post-tension slab. There are great foundations. As long as they are properly designed and constructed, post-tension slab will perform just fine. Drill piers. To put drill piers in the ground, you got an auger rig and you got a reamer rig. First, you go in there, you drill the hole with your auger. That's your shaft. Then you get a reamer like this. You open it up and you make the bell with it. It's the drill shaft out here. You got water in it. You can have up to about 3 inches of water in the hole. This is your piers, your bell, it's your steel. You bring it all the way up. You don't bend it into the grade beam. You bring it up and sleeve it in there. Put plastic over your steel in the shaft, and you put it in the grade beam. That way, when the slab moves up and down, it's not tied in there, and you don't develop cracking. Again, this is your pier, this is your bell. The steel comes over here, it goes into the grade beam. Here's your void box. Here's a typical slab. These are interior beams. They're about 12-foot spacing here. That's your piers. You got to put void boxes underneath all the grade beams, interior and exterior. All right, the structural guides. To determine pier depths, you got to know what's your moisture active zone depth. That's a zone at which soil changes moisture. Okay, and then the other concept you should know is zero movement line or movement active zone. What happens is the soils from here to here, above the zero movement line, they experience movement due to expansive soil and change in moisture. The soils below it do not move because of the surcharge loading. There's just so much load on it, they don't move. So that's a zero movement line. When you put a pier designing the ground, you got to design the anchoring deep enough below the zero movement line so that it will resist uplift due to expansive soils. The way you determine the depth of active zone is when you hit a sand layer, when you hit a rock layer, 2 foot below the lowest root fiber, when the change in suction is less than 0.02 P7 PF, when the liquidity index becomes vertical, depth of slicking sides, or depth of historical water table. Here's your moisture active zone depth. It's deeper near a tree root, tree trunk. So when you put a pier in the ground, you got to resist it by end bearing and skin friction going downward below the zero movement line. And then soils above the movement, expansive soil above the zero movement line will grab the pier, start lifting it. You got to anchor it down in here to resist uplift. The bell does not resist uplift because by the time bell gets engaged in the uplift, you've already moved up 2 inches, which means your superstructure is already experiencing cracking. So how you determine pier depths? Depending on your active zone. If your pier active zone is 4 to 10 feet, your piers are 8 to 20 feet. If your active zone depth is 8 to 20 feet, is 20 foot deep or deeper. It's 20 foot typically you put at 40 feet. In San Antonio, we have active zones of as much as 30 feet, so your piers can be as much as 60 feet deep. Austin, 8 to 20 feet. Again, at least 20 foot deep piers. So if you got a site out there in Westview, you got clay all the way down, your active zone is about 10 foot, your PI 50. Where's the pier going to go? What's the depth of your pier? Well, if active zone is 10 feet, the rule of thumb is twice the depth of the active zone. So it's 20 foot deep here. Here's another site. You got 0 to 10 foot, you got clay. Below that, you got sand. Your active zone is about 10 feet. Where's your pier going to go? About 23 feet, 24 foot. Because the skin friction in sand is lower than clay. So you're going to have to anchor it below the sand all the way down about 20 feet or so, 23 feet, to resist uplift due to expansive soil in the clay layer. What do we do in the floor slab areas? Well, we go a structural slab with void if your soils are expansive. You go a slab on fill to get the PVR to less than 1 inch. You can do chemical injection. If your soils are non-expansive, like you have in the woodlands area, you compact that soil and you pour a slab on the ground, and that's it. Structural slab, if you're doing a custom home builder, again, you see the tree in here. It's a typical custom home with a crawl space. Another custom home with a crawl space. That's how you build them. You got basically CMU walls all around. That's the garage. You park the car right there. But your floor slabs here are sitting above the ground with a crawl space underneath it. This is the typical crawl space. You put void boxes underneath these walls. Everything is supported on piers. These are your vents for your crawl space. This is a precast concrete panel type slab. You put your grade beam in. You just lay down your slab on top of it. These are precast panels. You grout between the panels. This is a house in Friendswood. This guy said, I don't want to have any movements. These are all oak trees here. The place is full of oak trees. Highly expansive soils. You drill your piers. You put a structural slab in there. These are your piers, your structural slab. Notice all these big trees around. You put down your slab. The whole thing heaves up, cracked to pieces. You know why? Because the structural engineer put the pier at 10 feet. And he was supposed to put it at 18 feet. He put it at 10 feet. The expansive soils grabbed the piers and pushed it up, and the superstructure cracked. The guy spent all this money for nothing. Here's another house in Braes Heights. Bunch of attorneys own it. 2 attorneys owned it. Structural slab system, expansive soils. No void boxes underneath these walls. Piers are at 10 foot deep. The whole thing heaved up and cracked the house. House in Seabrook. Piers are 8 feet deep. No geotechnical report. Crawl space. These are the actual builder's piers. These are their leveling piers. Wasted a bunch of money. Spent $33,000 to put leveling piers. This is sitting on basically a pedestal here, spread footing. So it's subject to movement seasonally. So we told them to have to take all this out. They shimmed it all like that. They had to go back in with helical piles and level the house and put the helical piles at least 20 feet deep. Structural slab with void boxes. And you can see that. These are void boxes. You put them inside the grade beam, also on the floor, in the floor slab areas. You'll put your steel on top of it. These are void boxes, cardboard material. They basically deteriorate when they get wet and create a void. This goes in the grade beams. These are the void boxes. Typically, we use minimum 6-inch void boxes. These are the void boxes in the grade beams. These are your piers. You put the covering page on them, sheeting on it. It's a protection. Put your vapor barrier there. Okay, here's another system here that's called a structural slab-on-grade construction. In this case, you don't have to use any grade beams. And so it's basically a two-way slab design. You dig your piers in, you put your piers in the ground, make sure they're deep enough. You put in your plumbing. You put your void boxes in if you need to, if your soils are expansive. This goes over the piers, all this steel and post-tension cables. These are PT cable. This is a temperature steel. Post-tension cables. Pour your concrete. You have no beams, nothing. You just put void boxes and you pour it in. It's a two-way slab system. Dallas area, they use terra firma, this type of terra firma foundation system. Let's see. You drill your piers, billet. These are your piers. Put your post-tension cables. Essentially, it's a post-tension slab on top of piers. These are the cables. These are basically where you can put your screws in. It's kind of like a, put it directly on top of the piers. This is your slab. You pour it. You pop these areas where you put that form in. You put a screw in it. You turn it. As you push it against the piers, the slab moves up. Okay, you can see that right here. You start turning the screw with this arm here. As you do that, the slab starts moving up because you're pushing it against the piers. You create a void under the slab. It's a structural slab now. Put a cap in there, put some polyurethane on top of it, and level it. It's basically a structural slab on piers here. Then you do grading around it. Here's another system of structural slab on grade beams. If you're in the heights area where your soils are non-expansive, you can go ahead and do this. Just go out there and with what they call pier and beam foundation system. You put your grade beams around and you put beams inside of it. These are wood beams. This is only good where you got non-expansive soils. You can also do basically spread footing or a strip footing grade beam type system with a crawl space. You basically put your columns here. You've got a spread footing here. Create a crawl space. You put your wall in. Here's a structural slab on spread footings. Again, you only use this in non-expansive soils. You cannot use this in West Hugh and Bel Air. You got to go out and use it in cypress wood, bridgeland, or something like that. Structural slab on post-tension slab. Okay, here's the deal. You go out there and put your post-tension slab in here in the ground, slab on grade. Then you put CMU walls all around it with a crawl space. So that's a post-tension slab with the CMU walls and a crawl space. These crawl space got to be nice and drained. You shouldn't have water sitting there. No trash. Not acceptable. Not acceptable. Bad design. Helical piles. We're going to see more and more helical piles introduced to Houston area for new construction and also foundation repair. There are great foundation systems. These are the helicals. This is the stem. You screw them into the ground. Helical system. This is the plate in here. Again, these are the plates. This is the stem. We've got a small surface area of the stem, so expansive soils cannot lift them up. Here are the screw piles. You just screw them into the ground and you leave them in there. You put them at least 20 feet deep. It's the helical piles. This one's got 3 plates on it. You grout them with concrete around them, top 10 feet to increase lateral pressure resistance. Lateral capacity of the piers goes up. These helical piles, if you put 12-inch concrete hole, you put the helicals in it and you concrete it. That gives you more surface area to resist lateral loading. You can also resist lateral loading with batter piles. This is your main pile here. This is a batter to resist lateral load. Batter pile. You screw them into the ground. This is your grade beam. It's helical piles. You put in your void boxes in. Put your vapor barrier. Pour concrete. Timber pile, if you're out there near Galveston, or out there near Ship Channel, or out there in Clear Lake, Seabrook area, you may have to use round or square timber piles. They'll treat it. These are the square ones. You drive them to the ground. You don't push them in the ground with the backhoe. Make sure you don't crack the pile as you drive them in. Fiberglass piles. Again, you use that in Galveston area. You drive them into the ground. You can fill it up with concrete or you don't have to. You can drive them in there. You can vibrate them in there. You can drive them in there. Pre-stressed concrete piles, if you're building a high-rise in the Galveston area, you drive these pre-stressed concrete piles. They got big surface area, very efficient foundations. You drive them into the ground. High capacity. These guys put these piles in an angle. The guy was an Aggie. Maybe that's why it's in an angle. So that's how they drop piles in some of the third world countries. That pile doesn't have much of a capacity. Some pictures of distressed beach houses here. Galveston after Hurricane Harvey. You can see what happened to the beach houses. The whole bottom washed out. The other type of foundation you can use nowadays is called conventional reinforced slab. It's not a post-tension slab. You got your square or rectangular shape. You got interior beams. These are the beam makeup. You got to put mild steel in it. You excavate your beams out there. Don't let these guys, plumbing guys, destroy your slab. Make sure they're doing a nice surgical placement of the plumbing. This is a nice way of putting plumbing in. Put the vapor barrier. Put your steel on top of, with chairs on top of a vapor barrier. Make sure you got chairs underneath your steel. Pour your concrete. Don't use rolled wire mesh. It ends up on the bottom. Pour the concrete. This is not acceptable. We need a lot of chairs. This is not acceptable. This guy doesn't have any chairs in here. When the steel ends up in the bottom, it doesn't do anything for you in terms of reinforcements, temperature steel or otherwise. So make sure you got chairs when you put your steel in there. You need about a couple of inches of cover on top of it. So we don't want the steel in the bottom of the slab. Look at this Bubba here. They're pouring the concrete on top of vapor barrier, and the steel is underneath it. So these idiots obviously don't know what they're doing. Post tension slab, you got interior beams, exterior beam. This is the beam schedule here. Sometimes you put mild steel in your beams. This is your cable, you drape it in. Typically your slab about 4 inches in thickness. This is a dead end in here. This is your basically PT makeup. You got interior beams, cables, chairs, the sink, bathroom areas, live end, dead end. This is a dead end in here. Okay, live end, you pull it from this area here. Here's the dead end on the slab. Your vapor barrier should be in touch with your bottom of your grade beam. It should not be hanging in there. Don't cut any of this vapor barrier. It got to be continuous. Otherwise, vapor is going to come through the slab, and it does that. It cracks your slab. So make sure your vapor barrier is in contact with the soil. This is not acceptable. We don't need voids underneath the vapor barrier. Not acceptable. Pump in your concrete. Your concrete slump should be about 5 inches. On big slabs, you go on there and level it with troweling. These are typical post-tension slab on ground. You go out there within 3 to 7 days, pull the cables. When the concrete hits about 2,000 PSI, you want to pull the cables. This is your jack. And this is how you pull it. You don't stand over here. You stay away. Make sure your jack's got properly calibrated. You measure your elongations. These elongations should be within 10% of what the structural engineer gives you. So the structural engineer says this cable needs to move 4 inches. If it moved 4.5 inches or 5 inches, it's outside the 10% range. So it has to be, there's something wrong with the cable. You paint it like this, and then you pull the cable, and then you measure the elongations. So when you basically, you put the cable in the ground, initially you pull it to 33 kips. After wedging seating, it drops to about 28.9 kips. With time, it drops to about 26.5 kips in tension. Okay? You cut the end. You grab the stressing pockets. Prior to installing the ground pockets, stressing pockets should be clean of dirt, oil, grease. There should be a good bond attained between the concrete and the grout. A bonding agent can be used to enhance the concrete grout basically connection. Get all the sand and grease out of there before you do the grouting there. The stressing pocket shall be filled with non-shrink, non-metallic grout as soon as possible after tendon stressing and cutting. In no circumstances should the grout pocket be left exposed for an extended period of time. Put the plastic cap in there and you put your grout cover on it. In no circumstances shall the grout used for the pockets filling should have chloride or chemicals that are going to be detrimental to the steel. You cover it like that. When you do out there, you got to check your form layout. Make sure it is correct before and square when you do concrete placements. This is not what you want to have. Affected trees. That's a big deal. You got to remember when you build a new house where there are trees on the site that you're going to cut or you're going to leave them there. You're going to have to design for the affected trees on your foundation. Okay, these big trees can cause foundation problems, especially if you use a post-tension slab. Okay, so if your site is wooded and expansive soils, once you cut those trees, you're changing the soil suction. Soil suction is basically described as the ability of the unsaturated soils to attract, retain water in terms of pressure. These are suction profiles. This is equilibrium suction. This is a dry condition. This is a swell condition, wet condition. When you have a tree on the site, this is your soil suction profile. Big area. This is a small area when there's no suction. So there's a lot of heaving going to happen on edge lift in Houston. So if you do a post-tension slab on grade with no piers, if your soil's got a PI of 40, your Y/M values are 1.4 and 1.6. When you cut that tree, it jumps to 5.3, 1.6. You can't design a slab that's within 0 years. You cannot design a slab with a 5.3 edge lift. If your PI is 67, your initial edge lift is 1.8 and 2.0. You can design a slab based on that. You cut that tree and you put a slab on top of it, your edge lift jumps to 10.8 and 2.0. You can design a post-tension slab with 10.0, 10.80 edge lift. This is a 0 year removal, 1 year and 2 years. After 2 years, it drops to 3.1 and 2.0. So what you do chemical injection. You go out there and you put chemicals injecting the site, and you get your Y/M values to 1.2, 1.4 in Houston. Okay, that's when you do 10 foot of chemical injection. I'm going to talk about chemical injection in a minute. Waffle slab system. These are another type of post-tension slab. You go grade the ground, mow the grass, grade, put a vapor barrier in the ground first. Then you put these plastic boxes in there and space between them. Then you go put your post-tension slab cables in there. You don't dig any grade beams. If you got plumbing, you just take a box out and put your plumbing in. Pour your concrete. That's what it looks like. Then you go grade all around it. It's called waffle slab system. We're doing them in Dallas, in Austin, California. They're using waffle slab type foundation system. No grade beam excavation required. If you want to extend your beam depth to reduce moisture transfer, you can cut this and put a vapor barrier there to increase your beam depth. This is a ditch witch. You dig a ditch there. And then you go in there, put your vapor barrier in. That's how you increase your beam depth. You can go up to 5 feet deep. We talk about chemical stabilization. This is what we call the lime slurry pressure injection system. In a lime pressure system, you get lime, you add water to it, you mix it in this tank, you inject it to the ground with these rods 10 feet deep. In Houston, this one is in College Station. We told them to go down 15 feet deep. It's a Walmart over there. Inject it. And what it does what's called cation exchange. It changes soil properties, it removes calcium, and it removes that sodium and potassium, put calcium in the soil, make the soil less expansive. Plus lime, what it does is provides a wall around the soil. It reduces the chance of change in moisture. So the change in moisture does not occur. That means the soil does not move as much. The chemical injection, this is the sulfuric acid type chemicals. You mix it in here, in these tanks with the hoses, and you basically inject it into the ground. This is sienna plantation, where you had a bunch of trees taken out. You inject it with the chemicals to a depth of 10 feet. This is an apartment complex in Braeswood. These chemicals go out there and alter the soil properties, just like the cation exchange. It also reduces the negative charge on the clay platelets. So the clay platelets does not want to accept as much water, so it doesn't absorb as much water, so it doesn't heave as much. This is the hole where injection occurs. Soil types where chemical injections are effective. If your soil's got a lot of cracks in it, it's effective. The more cracks, the better. That means the chemicals can travel. The less cracks, it's not as good. Houston soils do not have as many cracks. Poor construction practices. These guys are building houses in the swamp. You can see bad drainage everywhere, trash everywhere. These are post-tension cables. Bad construction. Poor drainage around the houses. Foundation makeup after the rain. These guys built this slab out there in Bel Air area. They put the vapor barrier in. They put their steel in. Got a rain in there. You washed up everything. Now to tear it down, do it over again. So in summary, it's important to do a proper geotechnical report. If this is the geotechnical report cost, the original contract, that's the change order. So the bottom line is you got to make sure your geotechnical work is done right. That way you won't have problems in the future. A lot of the stuff we talked about is on our website here. If you got some good pictures of the post-tension slabs or any other type of stuff we talked about here, send them to me. If you have any questions for this segment, we're done with this segment. Any questions? Okay, if there's no questions, it's 2:24 right now. We're going to come back at 2:30. We'll start with the next section. It's about construction. So we'll be back at 2:30, and we take a 6 or 7 minute break here. We'll be right back. Okay, we're live again. We're going to go into the quality control segment of our program, construction part. The last segment, of course, is going to be forensics, the failures of the residential foundations. You know, back in the old days, Romans used to build roads and subdivisions, and their inspectors used to carry a spear. If the contractor cheated, they used to hit him with a spear. And that's how they used to build their roads. Lasted for a long time. One more thing I was going to talk to you about was, you know, when we talked about when you cut a tree, you build a slab on it, a post-tension slab. You got to make sure you design that slab for that condition. 95% of the geotechs in Houston do not address that condition. And then 5 years later, you got foundation problems. So, you know, the structural engineers asked me to bring that up. Make sure you understand that when you cut a tree and you build a slab on top of it, the post-tension slab, you got to design for that condition. And if you don't design for it, you're going to have problems in the future. So that's kind of I didn't really say much about it, you know, when I was going through it, but most geotechs do not bring that up to your attention. We're probably the only geotech firm in Houston that brings you to your attention. Site prep. Remove grass, weeds, existing foundations, and paving. Establish good site drainage. Compact the subgrade soils to 95% standard Proctor density. So that's what the site looks like. Take out all the grass and weeds, compact with a sheep's wood or a steel drum roller. If your site is wet, you can aerate them. That means you open it up to dry up, fly ash it. If your soils are sandy, lime it when they're clayey. Remove and replace with dry select structural fill. Okay. In small area, you get small bags of lime and dry it up like that. So first you do basically clearing and grubbing out there. You start cutting all those trees out. Make sure you take all these tree trunks out. All the roots need to come out. And when you take these tree roots out, this whole area, that's area here, you got to muck it out, bring in fill material, put in lifts and compact it 95%. You can't just push dirt in there. All these areas are very soft. You put a grade beam in there, if you don't compact it, you're going to have foundation problems. Usually they cut a tree in here. You can see the root systems from a tree all over the place. So it's a big area. When you cut a tree out, this tree trunk needs to come out. You don't grind it down. You take it out. You don't push the dirt in there. You put it in there and lifts and compact it. All the organics needs to come out. This is not how you build a pad. This is a site near Kingwood. We had a hell of a time on this site. The contractor was building lots out here, and you go out there and pull out all these big chunks of, tree roots out of it. Horrible construction. Not acceptable. Look at the tree trunk out there in the field. All these tree roots needs to come out. I don't need any organics like that in the pad. All these root organics needs to come out. They decay, create voids, and cause settlement of your slab. Perch water table. We talked about perch water table when you have sandy soil over clay. A regular water table was about 15, 20 feet deep. Perch water table is near the surface. That's what it looks like. You can't build on top of perch water table. You got to treat it. When you cut that trees out, you get a rain, water just sits on top of the clay. It's called perch water table. If you build on top of it, you cut the grade beams, it gets filled with water. So if you got a perch water table conditions, the ground starts pumping. So if you want to build on top of it, you're going to have to improve that site before you can build on top of it. Okay, you can open it up to dry up, improve drainage. You can do soil mixing. You can do chemical modification, removal, and replacement. First, you can open it up. If you got dry season like we have now, you can open it up, let the sun dry it up. Then you can build on top of it. When it's dried up, you take the pumping out of it. Most of the time, that's not possible because you get rain within a week or two. So it's not really possible to dry it up. The other way is if you got site that's pumping, you go out there and improve drainage. You dig this, basically what we call bleeder ditches. You put them in there at 50-foot, 100-foot spacing, all the way to the detention pond. This allows the sands to drain in here, and you get the excess water out. Okay, you put rows of them in there. You take it to the detention pond or low area, and then you pump it to the neighbor's property. You can mix the on-site silty, sandy soils near the surface that are pumping with the soils in the detention pond or channels. If you got clay out there on your pond when you're digging it, get that clay and mix it with the sand or channels when you're digging them, and then put them on the lots. You get the clay soils, you dump it out there on top of the sand, you pulverize them in there, mix it in, you compact it, and then it becomes basically soil mixing. Again, that may not be possible sometimes. You may not have all the clay that you need. Usually you want to use 60-40, 60% clay, 40% sand and silts. You can do chemical stabilization. You can use fly ash or lime. If your soils are real sandy, you can use, fly ash. If you're, you still use lime too. You want to use probably dry lime, quick lime like this, dry lime. If you use lime slurry, it's got too much moisture in it. You can do fly ash. Here's a typical lot out there. That's north of Woodlands area. This is a lot. It's got a lot of sandy soils, pumping bad. And here's a lot. Lots of sandy soils out there. Real sandy. It's pumping. Sand. You get the fly ash in there. You dump the fly ash on it. You go out there and mix it all up with the sands on the top. Get in there about top 12 inches. Start adding water to it. You mix it in. You start compacting it. It becomes pretty hard. You check the density. You make sure you got enough fly ash in there. You check the depth. In this case, we want it to be 12 inches deep. When it turns purple, there's fly ash. Removal and replacement with good soil. You go out there, dig out all the sandy material that's pumping. You bring in clay material. Compact it in lifts and shipswood with a shipswood roller. Before you build a house, you got to proof roll the site. You get a loaded dump truck with dirt. It's loaded with soil. You go back and forth. Deflections like this is not acceptable. 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 Turns into, you put a slab on top of it or paving, it turns into a pothole. So it's very important that you go proof rolling. Make sure that you pick up all the soft spots and repair it. This is a custom home here. This guy's building here. This side was pumping. He digs out all the sandy soils, stockpile it. You can see all the sandy soils he removed. He brings in select fill, proof roll it, Get to the hard pan, start compacting it and check the density. You build up the lot. Disking, when you compact the soil, you cannot compact big chunks of soil. So you got to get up to less than 1.75 inches. So you use disking to chop it up to pieces, that soil, before you compact it. Compaction, if your soil is gumbo clay, you would use a sheep's wood roller. If your soils are sandy, use a steel drum roller. It vibrates and it compacts the sand better than sheep's wood. Sheep's wood is for clay. Steel drum roller is for sand. You grade with a dozer. Dozer is for grading, not for compaction. You seal it with a pneumatic roller. That's a compacted site. That's a pneumatic roller to compact it, to seal it. This is a pad itself. You compact it with a sheep's wood, then seal it with, in this case, with a steel drum roller. So when it rains, water will shed off of it. It's not going to go into the soil. This is, again, it's a pad here. It's got a lot of bird baths. It's one of our technicians, Mr. Patch. He rejects the pad. Too many bird baths. Lot drainage. You want to have positive drainage on the lots, away from. Good drainage away. We don't want water ponding next to the house. Positive drainage. This is Tabola here, out there in 59 north of the airport. Good drainage here. When the builders build the lots, they got a swale there to get the water out. All right, let's talk about compaction, testing, and quality control. Soil, concrete, and drill piers. When you build this pad in here to build your houses in there, this is Kingwood. You got to bring in fill material. This is select fill. This is the on-site gumbo. So this is the on-site material. You get a bucket of it, 50 pounds. And then you get your fill material from basically a pit. Pit's got different soils. You got sandy soils, you got clayey soils. Sandy soils, you get the good sandy clay material. Good sandy clay right there. Put it in the back of the truck, you send it to the job site. Or you put it in the pug mill, you load up the truck. This is your fill, it's your natural soil. You take it to the lab, you dry it up, chop it to pieces, run a proctor test, add different levels of moisture to the soil, and then compact it. You want to know at how much moisture you have to add to that soil for you to get the best compaction. It's called proctor test. 5.5 pound hammer, drop 12 inches, 18 blows per lift. You compact it with the machine. This is a 4-inch mold. You compact it, you know the volume of it, you weigh it. So you know the volume, you weigh the soil, you know the density. You develop this curve here. We say if you add 7% moisture, your density is 105. If you add 11% moisture, it's 122. Add 15% moisture, is 110. So you develop your maximum strength and maximum density when you have 11% moisture. This is the proctor curve, density versus moisture content, dry density, and here's your strength. So at your optimum moisture, you develop maximum strength. In small pads, you use jump and jack to compact the small areas. These are jump and jacks. You go out there and put in 2-inch lifts and compact it. You can get a small roller to compact stuff. This is your pad. These are your grade beams. You can tell your soil is compacted. You can see these cuts in here. That means the soil is nice and hard and compact. This is not good. Don't go out there and get your pad and build it with sand, especially in pearland when you got highly expansive soils with the PVR of 6 inches. You go out there and put sand on top of it. Then the sand will take the water everywhere and your slab starts heaving. Use your pad with select fill or on-site material. This is Tavola, Lennar. Use select fill out there to build your pad. Select fill. Do not use sand. Watch out those plumbing guys. They go out and destroy your pad. Not good. All these areas where you got the plumber tore up, you got to go behind them and compact with jumping jack. That's your final makeup should look like. Nice and clean with the, with the beams. The beams got to be clean and no loose materials. Take out all the loose materials. Make sure you got your compaction. That's how you run your density. You cut a probe in there. You drive your probe into the ground. That's the hole. You put your nuclear gauge source in the hole. Here you got the nuclear gauge at the tip. It's got a cesium-137. It emits gamma ray to a receiver in here, a detector. This is the source. The more it comes over here, the looser your sand is, the soil is. The less it goes over here, the denser your soil is. You check the density. Make sure you compact 95% of your proctor. Your proctor is 120 pounds at 11% moisture. So you want to compact your 95%, which is 115 pounds per cubic foot. At moisture content plus and minus 2%, which is at 9 and 13%. Grade beams got to be nice and clean. You can dig them out with a grade beam digger. That's a nice little trencher there. All these chunks and trash needs to come out. You get a guy in there with a shovel to dig out the stuff. Make sure there's no loose materials. That's a bad slab makeup there. Bunch of gumbo clays, loose materials, horrible construction here. It's not good. Look at your pier steel. It's all busted and really a bad construction here. You can see the grade beams in here. Piers. Get all the loose materials off your slab. Scrape all the loose materials. Make sure you got nice slab with no loose materials there. Put your vapor barrier on top of it. That's a bad pad there. Not acceptable. You cannot pour concrete here. All the tree stumps needs to come out. There's a 20-inch stump out there underneath the grade beam. 26-inch stump in the beam. 6 to 8-inch stump in the beam. Pecan tree right next to the foundation. All these things needs to come out. Sometimes you set forms out there in the beams. Make sure they're nice and straight. You put the tent on top of it. This is next to GHBA building out here, this church. They set the forms out there, let it sit. They got the plumbing in there. Grass starts growing. God knows if they compacted it. They put a church right there. This is the GHBA building. This is the new church. Correct field type and placement. This is Pearland, Lakes of Edgewater. The contractor goes in there, put a bunch of sand in the forms. You got a PI of 60 soils, heavily wooded sites, PVR of 6.3 inches. Bad construction. Don't do that. No sand. Bring in select fill or on-site material, gumbo. Compact around the plumbing. Don't put sand around the plumbing. No sand around the plumbing. This is Pearland again. These guys, this is the lot elevation right here. These guys go in there and put 30 inches of fill on top of it, not compacted. It's set deformed. This is not acceptable. Bad construction. And they said this is select fill. They got chunks of clay with sand in here. This is not select fill. Not select fill. They got all this soil here that's not compacted. That's almost 4 lifts that they didn't compact. Then they wonder why their slab is settling or heaving. We brought some of the samples in the lab. That's the clay and sand around it. This is not select fill. Concrete testing. Things are getting colder here. Okay, so you cannot pour concrete if the temperatures drop below 40 degrees. The mean daily temperature drops below 40 degrees. When you can pour concrete when the basically concrete is 50 degrees or higher for more than half a day. If you pour concrete when the temperature is low, you're going to get low strength gain with time, more void space, reduces the rate of cement hydration. You want to pour concrete when the temperature of the concrete is 75 to 100 degrees. This is the temperature of the concrete. You measure it. If it's hot, if you pour concrete when it's really hot, basically you're going to have increased water demand, accelerated slump loss, increased rate of setting, decreased tendency for plastic shrinkage cracking. You're going to have shrinkage cracks, difficulty in controlling entrained air, critical need for prompt early curing, decreased strength, decreased durability, non-uniform surface appearance, increased tendency for drying. So when it's hot. Here's some pictures of they poured the concrete and then it rained. Just washed out all the concrete. They're gonna have to jackhammer this out and do it over again. When you pour concrete out there, when you pump it in, you're gonna have to have a slump of 5 inches at the hose. You're gonna have to level it. Chairs underneath your steel, vibrate it. If you got a big slab like this, you may have to go saw cut it. You tell the concrete where to break when you saw cut it. You saw cut 1/4 of the slab thickness. So if your slab is 4 inches, you saw cut 1 inch. These are saw cut. Saw cut here, it tells the concrete to break underneath it. You saw cut at 15-foot spacing, twice the slab thickness in feet. So if your slab is 6 inches, you do it at 12-foot spacing. Slump test, you want to keep your slump test on your slab to about no more than 5 inches. So basically you put concrete in here in 3 layers, 25 blows per layer of the rod. Start pulling this up. In a few seconds, this should be less than 5 inches from here to here. If it's more than 5 inches, like here it's about 11 inches, too much water in the concrete, you reject it. Or if the slump is less than 1 inch here, you reject it. It's too hard. You know what this means? 5 gallons of water, add to the truck. So when you add water to the truck, for each gallon of water to 1 yard of concrete, 1 gallon of water will increase the slump by 1 inch. 1 gallon of water will reduce the compressive sting by 250 psi. 1 gallon of water wastes 25 pounds of cement. 1 gallon of water increases shrinkage by 10%. 1 gallon of water increases permeability by 50%. 1 gallon of water reduces freeze thaw by 20%. 1 gallon of water reduces salt scaling resistance. It increases the cracking by 10%, increase air content by 1%, increases segregation, increased water damage from traffic, increased dusting, increased finishing time for contractors and labor. So is 1 gallon of water, is it worth it of all expense? Here's when they added a bunch of water to the concrete. No durability, no strength. Big lawsuit here. They had to take the slab out. That was a big lawsuit case. Making concrete cylinders. When you get the concrete delivered to the job site, you put it in a wheelbarrow there, start putting it in the concrete cylinders out there, put it in 3 layers, 6-inch, 4-inch, 4-inch, 4-inch. These are 12-inch high by 6 inches in diameter. You rod it 25 blows with this rod. 3 layers, you basically scrape the top, make it flat, then put the cap on it. You leave it on the job site 24 to 48 hours for it to get hard before you move it to the job site, to the lab. You take it in a cylinder holder like this. If it bangs around, you lose concrete strength. You take it to the curing room. It's 100% humidity, 72-degree temperature here. You break it at 7 days and 28 days. At 7 days, you should have about 2,100 PSI for a 3,000 PSI concrete. 28 days, you're going to have 3,000 PSI. If your concrete is not good, you core the concrete, your slab. Make sure it's more than 4 inches. You bring it to the lab and cap it. You break it. Hopefully that concrete is going to have 3,000 PSI. Remember, the concrete, 28 days is supposed to be 3,000 PSI. There's not a good correlation between the cores and concrete cylinders. Concrete cylinders are just indication that your concrete has attained strength. Cores represent more representative of what the concrete is on site because it uses the temperature and humidity of the air around it to cure at the job site. One way that you can test the concrete to see if it's got proper strength, a cheap way would be using a Swiss hammer. You go out there and flatten the ground with this rock in here. You push it into the concrete. You push it in there's spring in there. It releases it, and then you can read here what kind of strength it has. It's not a very accurate system. It usually overestimates concrete strength. You need to really calibrate it with concrete cores. Another non-destructive testing is a Windsor probe. It's a gun. It's got a bullet in it. You set it up where you're going to do the test. You put the bullet in it. You shoot into the concrete. Based on the hole that it creates and the type of aggregates, you can estimate the concrete strength. It's called non-destructive testing. It doesn't cause, you don't have to core it or anything to do this. Drill pier observations, dry method of construction. The drilling with the shaft in here with the bell. We installed piers 3 ways. One of them is dry method. In this case, you drill a hole first. Then you have your reamer out there, opens up. You measure the depth. It's supposed to be 18 feet. Make sure it is 18 feet. You check the hole, make sure it's nice and clean. You can have up to 3 inches of water here. You check with the hand penetrometer, make sure you got the proper strength so that your bearing capacity is adequate. Use this hand tool here. You swipe it around, make sure you got the right size bell. If your shaft is 12 inches, it should be 12 inches to make sure you got a 36-inch diameter bill. This is how you basically swipe it all around. Put your steel cage in there. You pour concrete, make sure it doesn't hit the sides. It doesn't hit putting clay in there. This is dry method of construction. You drill a hole, you put your cage in, you pour your concrete in there. Next one, if you got sandy soils on the side where you're going to have caving problems, you use casing. You drill the hole, you set your casing in, you drill inside of it, you get the soil out, you check with a hand penetrometer, you got the proper strength. You put the reamer in there, you make your bell, put the steel cage, you start pouring concrete, you pull out your casing, go to the next hole. You can use trimmy to pour concrete. It's like a funnel. It reduces segregation of the concrete. Now you're going to use a slurry method of construction where you have sandy soils and shallow water table, because casing does not reduce the water table situation. So you're going to have to get bentonite, mix it with bentonite and water. It keeps the hole open. Okay, you got a unit weight of about 70 pounds per cubic foot. This is the tank mix. You dry the hole, drill the hole. You put synthetic here, slurry. You put your steel cage in. The slurry keeps the hole open. This is your slurry in here. You pump concrete in there. And the concrete unit weight is 150 pounds per cubic foot. It replaces the slurry. The slurry sticks to the sand. It keeps it from caving problems. Plus, you got the hydrostatic pressure to keep the hole open. You drill the hole. You introduce the slurry. You put your cage in. You pour concrete with a trimmy. Okay, we're finished with this segment of the presentation. Any questions? Send me some pictures. If you got construction pictures, please send me. If you got interesting pictures of the construction, I can always use them for training purposes. We're going into the next segment of it. Is forensic engineering part. We're going to take a break here for 5 minutes. It's 3:04. We come back here about 3:10 for the next segment and final segment of which is probably the most interesting part of this presentation, is the forensic part of the presentation. That what we do when foundations starts failing, how do we determine that? So any questions? If no questions, we'll shut it down. We'll be back in about 6 minutes. Okay, looks like we got a question here for Tad Scott. He says, what type of foundation do we have at your residence? I have drill piers with slab on fill on piers. My house got non-expansive soils over there where I have, so I use piers out there because it's a better foundation system. So slab on fill on piers. All right, let's go to forensic evaluation of structures, residential. We got some hairline cracks here on this house. Retaining walls. Hurricane Harvey kind of busted this wall here. This is the wall in San Antonio that failed. And you can see all the cracks out there. Basically, they didn't check the global stability of that wall. So the wall failed and took the backyard of these houses. 250 houses were impacted. See the AC units. Here's another retaining wall in Conroe. That's Lake Conroe out there. When we had the drought situation, these guys wanted to dig in front of their houses to connect to the lake so that they will have some kind of a, they can put their boats in here. As they did that, they didn't check for the retaining walls here. The retaining wall starts failing. They want to connect this channel to this channel here. All these retaining walls in the backyard starts failing. This is the crack in the backyard. They had expensive pools here. The pools have started to move. The flat work start cracking. Geologic faulting. I get called last week from a builder. They're trying to build a house in Hedvig Village next to a fault. I told them don't build a house on a fault or next to it. But the lot was cheap. We wanted to buy it. This is the fault going out there and cracking up the house. Storm sewer leaking. As the storm sewer leaks, causes basically creating voids underneath the pavements and start collapsing. Building failures. This is a building in China sitting on piles. You see the piles right there. Fell down. They cut in front of it. They stockpile it here. It caused surcharge and basically came in and had a slope failure, cracked the pile foundations. The whole thing failed. The Italians can do wine, but they cannot do buildings. We don't use their geotech guys. The building settles. All right, look at this design here. Got a problem there. Got a problem here. This is Rice University with their CMU blocks. More cracks in the CMU blocks. More cracking here. Brick cracking. Cracks out here. This is Strand to Galveston. Separation in the brick there. Cracks in the brick. Cracks in the brick. Here's a church structure out there in Bel Air. These are the cracks. Separation on the house. Cracks in the exterior beam. Floor slab cracking there. Flat work cracking. That's a Montessori school out there on Derry Ashford. That's Derry Ashford there. Pavement structure failure. Pavement failure. There's no steel in here. Sheetrock cracking in the living room. More sheetrock cracking. More cracks. Tiles separating. Tiles cracking. Moisture coming to the slab. Absence of good poly underneath the slab. You see the moisture coming through the slab there. Moisture coming through the slab. This is a warehouse building here. The contractor put vapor barrier underneath this segment, but didn't put it here. So what happened was the moisture come through the slab, and he was complaining about his slab being wet all the time. Sheetrock cracking. This is a medical building in Stafford. It's a bathroom in a school in Tyler, Texas. City of Houston, command station, police. The floor slab is heaving. The wall doesn't have any place to go, so it's bulging up. Medical center facility. Bedrooms, sheetrock, the ceiling. Doors not square. Doors do not close. Doors not square. Here, the window shattered here on this medical building here. Door doesn't square, close. That's a Montessori school. The door doesn't close. Hovering wall in the medical facility out there in Stafford. That's a corner cracking on the grade beams out there. That's because of absence of bond breaker between the brick and the concrete. Again, you see the corner cracking here. Absence of bond breaker between the brick and concrete can be fixed by basically using a bonding agent and putting non-shrink grout and replace it. See the crack here? There's a little lake next to Dallas. This thing starts dropping. Let's take the house with it. In the Harris County area, we have a lot of dispersive soils. These soils wash out when the rains hits them. Very, very erodible type stuff. They develop these little tunnels and jugs in there. You can see the dispersive soils there. This cop was chasing out there along the detention pond, fell into one of these holes, broke his back. They sued everybody. I got the developer and the homeowner association, everybody, the geotechnical engineer. Pool failures, a lot of pool failures around Houston. Crane failure. These guys were delivering 2 yards of concrete, medical center. The crane flipped right here because the soil was not compacted. The outrigger went into the soil, it just flipped. We see a lot of bulkhead failures in Houston. Lake Conroe, Lake Livingston, Galveston Bay, Seabrook, Colorado River. Bulkhead failure, the whole back anchoring system was not adequate. Slope failure, this is a doctor house out there in Memorial. They put concrete bags, make the slope heavier, so the whole thing failed. See the backyard failure, parking lot failure. Landslide. Houses sloping down the slope. Buffalo Bayou. This golf course here, they wanted to stabilize the Buffalo Bayou banks next to the golf course. So they put GeoGrid in there, geotextile. Grass will grow through it. But they didn't check for global stability. The whole thing starts washing down. And they had to start having slope failures. You can see the golf course here. You cannot play past this red line here. There's a bunch of attorneys here. Here's the golf course. That's right there at Buffalo Bayou, San Felipe. Beautiful place. Very nice golf course. You can see that here. The whole slope has failed. Efflorescence, you go out there and look at some of these houses, you can see this white powdery stuff basically dried up on top of the concrete, on top of the brick. called efflorescence. Efflorescence is a fine white powdery deposit of water-soluble salts left on the surface of the brick as water evaporates. To have efflorescence, you must have soluble salts that are in the wall. There must be sufficient moisture in the wall to bring the salts to the surface and have it in a solution. There must be a path for the soluble salts to migrate through the surface and where they evaporates and depositing the white stuff. Most of these efflorescence sources are alkali, sodium and sulfates, potassium sulfates. One thing we need to put in the specs is when you build some of these walls out there with a brick, with the mortar that you use should be less than 0.6% alkali in cement. So what is failure? Failure is defined as a foundation, structure, component, or facility that does not perform as intended. A failure does not have to involve collapse or catastrophic event. Some examples of the failure are a foundation that exhibits excessive differential movement, parking lot that ponds water, roof that has excessive deflection, masonry wall that cracks because of lack of joint spacing, expansion joints, basement walls that leak, pools that are moving, slope failures. Most of the failures are not on the evening news, but they are important to the building owner who has to deal with it, and to the contractor who has to repair it, to the engineer that gets sued for faulty design, and to the attorneys that make the money. The method to determine the causation for failure is we state the problem, perform observations, formulate the hypothesis as to cause a problem, test the hypothesis by observations, analyze the results, make final conclusions. And then part of the development of conclusions and all that is a damage model. How much is it going to cost to fix something? It's called damage. How much damage cost? Qualification of the forensic engineer. Got to have formal education, experience, licensed, active in technical societies, truthful, objective, avoid conflict of interest. Must be like a detective, someone whose job to discover information about crimes and find out who's responsible. You have to be able to think outside the box. You have to enjoy digging for the truth. Must be a good communicator and be able to report on presentation of clients. So we have a matrix here at the causation for failure. It's usually design, construction, bad materials, maintenance, wear and tear. Bad design is a wrong geotechnical report, inadequate structural design, bad construction, didn't follow the plans and specs, the materials used were wrong, bad drainage, got a lot of trees there, sewer leak, plumbing leak, wear and tear, inadequate geotechnical report. If the site conditions does not describe the site, let's say site is near a big ravine and nobody says anything about it. The structural guy doesn't know. He doesn't go to the job site. So he will design the foundation not knowing there's a ravine next to it. The geotech guy needs to say that in his report and take some pictures and show the site that's got next to a ravine. Incorrect bearing capacity values. Okay, in places such as woodlands and bridgeland areas and Cinco Ranch, they got sandy soils near the surface. These sands become saturated. So you're going to have a saturated bearing capacity. You cannot just use, high bearing capacity in these areas. When these sands become saturated, the building settles. Footing depth. We get a bunch of wrong footing depths. On the sites where you got trees that you got and highly expansive soils, your pier depths in Houston should be about 18, 20 feet deep. You cannot go put piers at 12, 14 feet deep. Inadequate PTI values and BRAB values. This is what I see a lot. Most geotechs don't know much about PTI. So the PTI values they give are wrong. It's very important when you're slab design, when you do post-tension slab, you gotta have proper PTI values. Absences of recommendations on maintenance. You need to have foundation maintenance. Just like you maintain your car, you gotta maintain your foundation. Inadequate testing of the soils. You don't run enough tests. Inadequate estimated movement values. You don't give them PVR values. You don't give proper PTI values. Inadequate information regarding perch water table. If you got perch water table, you need to talk about it. Inadequate structural design. Did not discuss foundation as a risk with the client. If you're a structural guy and you're doing a custom home, you got to get those with the owner and tell them, look, if you don't want any movement, you got to go with a structural slab with piers, with voids, with crawl space. Costs money. If you want to have potential risk of movement, you go with a post-tension slab. Let the owner make that decision. Unfamiliarity with the proper design method. Just last week, structural guy wanted to put the piers at 12 feet on a site with heavy, highly expansive soils and trees. Doesn't know what he's doing. Foundation design without soil report. Just this month, nice big church project. No soil report. Everything is failing. And the structural guy did not insist to get a soil report to design a foundation. That's how you can lose your license. Excessive pier spacing, undersized piers. Grade beams got to be continuous. You cannot have short, cut off grade beams. Misapplication of designs to slope sites, sites on active faults, using wrong type of foundation for the soil conditions. The engineer record should have adequate information, including drainage, slopes, existing trees, future trees, and vegetation prior to foundation design. So the engineer record should have all this information. You cannot just go out there and design a foundation and the thing fails and say, I'm not responsible. You are responsible. Inadequate construction. You go in there, your grade beam is supposed to be 28 inches deep. You go measure it, it's 24 inches deep. That's a cubic function. Your stiffness is reduced significantly if your grade beams are not deep enough. Okay, you measure the beam depth. Next, you measure the beam width. If your beam is supposed to be 12 inches, but it's only 10 inches, you're reducing the stiffness. Okay, so it's a bad construction. You don't follow plans and specs. You measure the width. If you're using piers, you make sure your piers are right depth. Okay, so if it's supposed to be 18-foot piers, you measure the bell's got to be at 18-foot deep. This is your shaft. That's where your bell is. Okay, you measure the distance from the tip of the shaft to the bell. And that tells you what size bell you got. Make sure your piers are deep enough. You excavate the pier if you need to. You see the void here? The pier is too shallow. The expansive soil is grabbing the pier and pushing it up. If your piers are connected to the grade beams and this area is heaving, that means your piers are too shallow. This is the house out there in Brace Heights. Got piers at 10 feet. The whole thing is heaving up the slab. If there's a void between your pier and your beam, then that means your piers are deep enough, but your wall is moving up because there's no void boxes there. Here's a sound wall in Pearland, Texas. You can see the piers are coming out. Here's the piers are coming out. Instrumentation. You can put crack monitors here to see if the cracks are moving and what function as function of time. Here's a crack monitor. It tells you how much it's moving and how as a function of time. It's a crack monitor there. Non-destructive testing. Perfometer, if you want to know there's a steel in your slab is, and what spacing, you can use this device here. It uses eddy current. Tells you where your steel is, how deep it is, and what size of steel you have. You can also use what's called ferroscan. You run it on the slab, and it tells you where your steel is, what size it is, and how deep. The accuracy is about 4 inches thick. Here's it says where the steel is, about 10 inches and 8.5 inches. 8.5 inch and 10-inch spacing. Okay, this is a number 5 bar. Here's one of the clients that would have this metal building here. They want to know if the slab inside had steel in it. So we went in there and we took blocks, areas. We checked for steel. We found out the steel spacing was 10.8, 11, 13 inches in X direction, and 11.2, 13 inches in Y direction. The specs call for 10-inch spacing. And the concrete is supposed to have been 2 inches below the surface, and they were 3.5 inches, 3.2 inches, 3.5, 2.9 inches below the surface. We don't want the concrete, the steel all the way on the bottom of the slab. That's not a good deal. You can use sound velocity to calculate the concrete thickness. So on this project, you send the sound velocity through this device here. It hits the concrete. It sends sound through it. Sound travels at 10,000 to 14,000 feet per second for good concrete. And you can read the thickness here. So here's a warehouse floor slab. We calibrate this machine with the cores. We core the concrete. It's about 5.5 inches. We put the machine here. We calibrate it. We actually measure the concrete thickness in here. You can see 4 inch, 5.7 inches. The concrete should have been 6 inches, but at many locations it's 5 inches and 4 inches. The tolerance for something like this is about 1/4 of an inch, 0.25 inches. So most of the area that are in pink here, they failed. We also checked the parking lot then. We core it, we calibrate it, and we found the area where the concrete is supposed to be 8 inches. In the parking lot, there's 7.8 inches. 7.9, 7.9, 7.8. This is within tolerance. 6 inches where it's supposed to be 4.98. These are not within tolerance. So we had a lot of areas within this thing here that was not within tolerance. Then we went in there and did borings. We did the borings next to the trees to see what kind of soils were on the buildings. The borings were next to the trees to give us root fibers. Root fibers tell us where the depth of active zone is. We also cored it inside the building. We noticed the core dropped. There's a void under the slab. So there's a crack out there in the slab. We removed it, checked it. We put a camera under the slab. We saw there was the pad is separated from the slab itself. This is the crack. You can see over here, we couldn't find vapor barrier there. We found a little bit of vapor barrier right there. But the pad had settled away from the slab itself. The slab was sagging and cracking. This is the crack right there. We'll also check for the soils. There's supposed to be 4 foot of select fill under the slab. There was only 2 foot of select fill. So we look at the soil. Here's the house out in Seabrook. Went in there and we drilled it. See what kind of soils we have. We have a bunch of clay soil, gumbo. They said the piers will be 8 feet deep. We calculated the pier is supposed to be 18 foot deep. We check elevations on projects. This is a Stanley tool. You go out there, run elevations throughout the whole slab. And you get the elevations on it. This is Michael Scholar, by the way. Another way you can tell what the slab elevations are, and when you do construction of a slab, you put these cables in there in your grade beams before you pour the concrete. It's called steadfast system. You pour the concrete. This cable has got sensors at 10-foot spacing, and you can measure the elevation change as a function of time digitally. So you can develop contours of your flash slab if it's moving. So it's an automatic continuous thing that you can put in your slab. If you want to do that, you would know for a long time, monitor it and find out if your slab is moving. You don't have to go inside. You can do it basically remotely, find out how much movement you got on your slab. Called steadfast system. If you got a house like this and you get elevations like this, is a minus 2.4, elevation 0.2. So this side, is it heaving or this side is settling? Well, it's a brand new construction. On a new construction, where you got expansive walls, it's heaving. So this side of the house is heaving. This is a medical facility. It's basically elevation 3.75 here, elevation 0.5 here. So it's 3.25 inches elevation difference. It's sloping this way. This is another building in here. These are the elevations on the slab. Elevation 1.4 is the high point. Elevation minus 1.8 is the low point. A differential movement of about 3.2 inches. These are the heaving part. These are the low areas. There was no soil report for this job. The whole inside the building was all cracked up. That's a school project. You go inside of it with HISD. Your elevations, here ranges anywhere from 375, 3.8, all the way up here. These are minus 3.75, minus 1.13, minus 0.5. So you got as much as 4 or 5 inches elevation difference along this slab here for the school building. This is a building out there on 11,000 Richmond Avenue. Tilt wall building. The site was heavily wooded prior to construction. If you go look at it, the whole soil is expansive soil, heaved up. They cut the trees. The building heaved up. Elevation 3 and a 3/8 here. You go inside. A lot of these offices are cracked up. The sheetrock cracked up. Doors don't close. A lot of foundation problems. It's a three-dimensional, basically dimension of the slab, how it's warping because of the expansive soils and poor design and construction. Here's some concept for structural engineers that are listening. Tilt slope. Tilt is basically a planar with rotation measured over the length of the foundation, y over x. Y over x. Slope is the differential elevation between 2 points divided by horizontal distance. TRCC, Texas Residential Construction Commission, says you can have 1% tilt, same as ASCE. So that's 6 inches for a 50-foot wide slab. So it gets 1% tilt allowable. This is a house at foundation problem. You plot the elevations, it's all linear, parallel to each other. It's tilting. Deformation is a change in shape of foundation after the original foundation construction. Deflection is the maximum deviation from a straight line between 2 points. Deflection ratio is deflection divided by horizontal distance or which the deflection occurs. This is the correct elevated deflection. This is not. So you need 3 points to measure deflection. This is the house out here. This is the floor slab elevations. You should get section BB in here. You look at the elevations on it. Like that. You see this elevations. The actual elevation is L over 563 is less than elevation L over 360. So it's less than 1% tilt here, 0.38%. And the we allowable is 1 inch in 30 feet deflection, L over 360. So is L over 563 is a smaller, therefore it passes. You get that other section in here, you plot it. The deflection is L over 318, which is basically is higher than L over 360, so it fails. The tilt is 0.13%, less than 1%, it passes. These are TRCC standard performance. TRCC is not around anymore, but a lot of lawyers use that to evaluate foundation failure. If your slab cracks more than 1/8 of an inch, it's not acceptable. Your flat work cracks more than 1/4 of an inch. If your flat work separation is more than 1 inch. If your stairs have got 3/8 of an inch settlement. Carport garage settlement more than 3/16. Sheetrock 1/32. Brick 1/8. Joints in the gaps in the brick more than 1/4 of an inch. One way you can, of course, reduce the movements. Use a sprinkler system all around the house. Put space between the driveway and exterior beam. Have positive drainage. Do not use sand in the forms. Remove the expansive soils and place non-expansive soils to get your PVR less than 1 inch. Here's the building in here. It's grass here. It's concrete here. This part of the building is going to move. This area is not going to move, so you're going to see cracking right there. This part of the building is going to move. This part is not going to move, so you get cracking here. Now, this blockbuster, you got grass all around it. So you're going to have uniform moisture everywhere. So there's less potential for movement. When you put a driveway in, you put a space between the driveway and the house so that the house is going to have moisture, uniform moisture around it. This condition is not good. You have basically got driveway right next to the foundation system. This guy's over here that put concrete everywhere all around. So that's good. Once you cut the trees, the ground's going to heave up, but it's going to stop eventually. So there's no change in moisture, so the building is not going to move as much anymore. Benchmark. A lot of the measurements we make on elevations are relative to a reference point, but that reference point can move. If you don't want your reference point to move, you put a benchmark in. You do a benchmark, you drill a hole about 12 inches in diameter, you put a helical pile in it, about 20 foot deep, okay? So you go in there, the helical pile itself be 25, 30 feet deep. You put in a hole that's 20 feet deep. That's a helical pile. You put it in there. You separate the pile from the surrounding soils, but the PVC with the PVC pipe. You put the PVC pipe in there. You put grout around it. This pile has got a centralizer in it, and it's isolated from surrounding soil. It's down below 20 feet into the ground. So it's fixed. If the expansive soils cannot lift it because you got the PVC pipe and it's installed below the active zone. So use this as a reference point. That's a zero reference point. You go out and measure the elevations of the house. So you get a bunch of elevations here. You get sections like this, A, B, B, C, C, D, D. And you can go out there and see the slab movement as a function of time. Okay, this is the slab itself, and you get November 2003, August 2004, 2005, and you can see how the slab is moving. Perch water table, when you do forensics, you go out and check to see if you got the first perch water table next to foundation. On a lot of these jobs, you dig a hole, water starts gushing in. There's a lot of water underneath these foundations. So perch water table, you got sand over clay, just a bathtub situation. You dig your beam, it's full of water. If you want to know where the water is underneath your foundation, you put in piezometers. You drill a hole in the slab, you put this PVC pipe, which is perforated, allows the water to flow through it. You put sand around it, you put it in the ground, then you can check to see where the water level is as a function of time. You can go out there and, you know, in this case, it's 7 foot deep in this area. These are piezometers just to see where the water level is. You can check it all the time to see if there's water fluctuation under your slab. It's the cap of the piezometer there. You can also, you check your slab with lift-off testing. There are cables inside your post-tension slab. The purpose of lift-off testing is to verify the design force in the tendons has been achieved. On occasion, a situation will require a lift-off to be performed. This could be due to elongations being out of tolerance. In addition, sometimes specifications require verification of the force in tendon. You want to know your slab over there, the tendons are good. So you go in there and expose your tendon tip. You grab the live end and start pulling on it. You get it down to about 0.85% of the design load, about 26.5 kips tension. That means your cable can hold the load, so you're okay. If your houses, your buildings got brick, you got to put brick joints in it. Otherwise, you're going to have cracks everywhere. It's got only one brick joint for this whole building here. It's a bad design. It's one joint. This building does not have brick joints, so it's cracking up. No brick joint. Here's a good brick joint right there. It's a good brick joint. Brick joint, open it up here. Here we had to saw cut a brick joint to reduce cracking. We typically put brick joints at 20-foot spacing. Why do we need brick joints? Because brick and all building materials expand and shrink with changes in moisture and humidity and other environmental conditions. Because these materials have to move at different rates, because nature will put them in if you don't. You got to put brick joints when you got periodically in long walls and offset in walls, where short run of masonry runs into the long runs, at outside corners where different materials meet, at junctions with different functions or different heights. Well, another thing we do when we find out, checking out on forensics, to see if the material that they used was good or bad. For example, if the contractor used good concrete or bad concrete. We check for fill properties, if they use sand or they use select fill. If they're steel grade 40 or grade 60. We core the concrete. We check the thickness. Check to see if there's a steel in it. We break the concrete. American Concrete Institute, ACI, says concrete in an area represented by core test shall be considered structurally adequate if the average of the 3 cores have at least 85% of F''C. F''C is the design strength, and no single core is below 75% F''C. Additional testing of the cores extracted from the location represented by erratic core results shall be permitted. So if your slab is supposed to be 3,000 PSI, 0.75 is 222.50 and 0.85 is 25.50. What it says, ACI, is that when you do 3 cores, or 3 cores, none of them should drop below 22.50. An average of 3 cores should not be 25.50. So if average of 3 cores drops below 25.50, your concrete is bad. If one of the cores breaks below 22.50, your concrete is bad. Let's say your string passes, but you still got a bunch of cracks in your slab. You do petrographic analysis. You get cores of your slab. You get a slice of that core, That's what it looks like. You put it under a microscope. You inject it with blue dye, which you can see the water cement ratio in the slice. Your water cement ratio should be about 0.4. Here is 0.55 to 0.6. That means your concrete was wet. We check for air voids. The core has some parts of it's got air voids, some parts of it's got no air voids. So it's not uniform placement of air voids. We check on it, we see calcium hydroxide in here. Okay, around the core, some of the paste. But where we look around the paste here, we see dark black clay material. That means your aggregate was dirty. Okay, and we also saw cracks out there in your aggregates. Pass. So you can do petrographic analysis, check for entrained air, check for dirty aggregates, check for fly ash, and check for chemical attacks in your concrete. Do you have helical silica reaction? Helical silica reaction, ASR, is a reaction between certain aggregate types with cement. So usually with petrographic, you can see these things and see why your concrete is cracking. If you have high water cement ratio, you got too much water in your concrete. So it's cracking because it just evaporates. So it shrinks, so it develops a lot of cracks. Or it's called ASR, which is a reaction between certain type of aggregates with cement that forms a gel that can cause excessive expansion, cracking, and pop out of concrete. So you can do petrographic. We check for drainage around the house. This should be the positive drainage around the house, not a pool situation. This is not acceptable. You don't want to have a low area around your house. When the developers, when you develop a subdivision, they have these swales between the lots for drainage purposes. Positive drainage. Positive drainage. Positive drainage. This is not acceptable. The backyard is full of water, not acceptable. Not acceptable. Not acceptable. We have these swales for water to drain. Don't fill them up. If you go out there on Gessner, you got on Gessner, these landscape architect guys design all landscape to get negative drainage towards the building, apartment complex. West Road, these guys are building these mounds over here. You get negative drainage towards these houses. If you put sprinkler system, make sure you put them all around the house uniformly. Don't just put them in one location, just the front. That means the front is going to heave up and down, and the other sides are not going to heave up as much, so you get cracking. Sometimes you put a skirt around the building to reduce movement, and you put sprinkler systems. Bed liners. Some people go put bed liners and go in there and put topsoils and expansive soils. Bad construction. The bed liners, the gravel, all detrimental. They hold water and cause heave and cyclic movement of the foundation. The bed liner is bad. You fill it up with gravel. You got a bathtub next to your foundation on expansive soils. Again, you got granule material with bed liners here. And negative drainage. Bad design, landscape design. This guy's got a fish pond in Pearland next to his house. It keeps that whole area wet and causes movement. AC unit, these are the AC units in Tanglewood. The condensation caused this side of the house to move up and down. These are AC units. Lots of condensation units. Condensation. All this water, if it goes in the grass, and if you got expansive soil, it can cause heave. Gutters, you're gonna have them actually go underground. If they're draining like this with no splash boxes, they're gonna create holes. You lose bearing capacity. Allows water to go underneath the foundation. And soft soils cause a lot of problems here. Again, bad guttering system, low area. Water sits over here, causes movement. Bad guttering. Get that water away from the house. These 5 feet away. Underground drainage. Here's an underground drainage coming out of the curbside. Here's a Olive Garden gutters coming over here, going underground. Here's a building that's got a sloping roof. Roof is sloping this way. They only have gutters on one side, on this side. These are the gutters. This side of the building was heaving up and down because it's always wet because of the gutters. Non-uniform moisture conditions. This is a house on 1488 and 45 in that area. Jacobs something or another. I forgot the name of the subdivision. And you can see this house got positive drainage. However, they got these bed liners here with the perch water table. Water is going under the slab. They're holding the water next to the foundation. And it's saturated. Inside the house kind of smells. And so don't put bed liners in there. Get that water out. Here's the absence of guttering system. The area next to the foundation is all basically settled away. You got a little low area. When it rains, water sits there. This is Pecan Grove Plantation out there in Fort Bend County. 60 houses over there had foundation problems. Gutter overflow. Try to put a lot of gutters and the good volume so that when rain comes, it doesn't overflow and cause heave on one side of the building. If you just a lot of water on one side, you're going to have heave. This is a depression here that somebody dug out. Guess who did it? The hot doggy there. And what happens over there is this low area when it rains, gets filled with water, and if have expansive soils, causes heave of the foundation. Here's another one under the AC unit. If you have areas where there's no grass can grow, the gutter comes in, make sure you got positive drainage everywhere. The drainage should be established with a clay, not with sand. If you have low area here, water is going to sit here and you're not going to see it. Use underground drainage system. The gutters go underground. Put some area drains here to get that water just sitting in the gravel, causing heave of the expansive soils. Get that water out with area drain. These are area drains. You put them around the building to get that water away. Olive Garden Chondro. I was out there eating lunch a few years ago. It's built with rock and mortar, very rigid structure, bed liners and gravel. If your soils are highly expansive, and when it rains, water is just going to sit here. Causes heave. So it's a really bad landscaping situation if you have highly expansive soils. Rigid structure with bad landscaping can cause cracking. So the manager says, "Hey, why are you taking pictures?" I said, "Well, I'm taking initial pictures of the building that was brand new so that when it cracks, we know how it started." Bad landscaping architecture. Check the soils in the planter area for topsoil. Do not use topsoils where you got expansive soils. When you go into planted areas next to these buildings or a house, if you dig out that soil right there, if it's all sandy, topsoil, it can cause perch water table. Water just sits there on top of expansive soils. So if you got expansive soils, if you use topsoils in your planter areas, you're asking for trouble. We need positive drainage away from the house. If you got a hole here, you fill that with sand for leveling purposes. When it rains, water sits here, not going to go anywhere, feeds the expansive soils, causes the house to move up and down. So make sure all your grading done is with clay. Then you put 2 inches of sand for grass to grow. This is a house in Bel Air. They had this decking in here. This back of the house was heaving up. You remove the decking, you see sand underneath it, just holding the water there, perch water table on top of the gumbo clay and causing heave. Houses on the slope. If you go out there in Memorial area, a lot of these houses next to Buffalo Bayou, they're on the slope. There's a lot of movement and failures on these Buffalo Bayou slopes. They got really sandy materials, gets saturated, things starts moving, start cracking. These columns, it starts deflecting, high levels of moment and shear, and crack the whole columns. It's because wimpy columns in here for the houses on these slopes. Look at these columns. It's very poorly done. Multi-million-dollar houses on a slope. Houses are, basically sliding down. Here, me and Carl Bracken up there in Conroe. I know that's Tomball. The whole backyard of the slope has failed. If you put piers out there next to a slope, make sure piers are deep enough to resist lateral move due to slope failure. This is a Arlington Court subdivision out there next to Memorial Park. Look at this space between houses. This space about 2-3 feet wide, okay? You go to the back of the house, they got this ravine there. They got this retaining wall there, monopile system, trying to hold the back of the house. They got this patio that's separating from the house itself, this patio. And when they put concrete bags, made it heavier. And the whole thing is separating from the house. Since there was no access to the backyard, we couldn't do much. So we told them to sell the house as is and get out of Dodge. This is a doctor house in Memorial next to Buffalo Bayou. The back of it was terraced. They start having slope failures. The whole back of the slab starts moving. Develop cracks everywhere in the house and outside the house. They had to tear down the house, build a new house with deep piers. So when you build a house on top of the slope, you're going to have the global stability. Your foundations should resist global stability. The factor of safety here should be more than 1.4. Otherwise, you're going to get creep and movement and slope failures. Here's a swimming pool. People love swimming pools. I got one in my house. This is a natatorium there. World's largest pool. Chile, $1 billion. Look at that pool there. Well, let's go back to Tanglewood here. You see this side of the pool? Lower than this side. Why's the water coming up here? Well, what's happening at this side of the pool is heaving up. This is a floating pool, not properly designed. About 95% of the pools in Houston are not properly designed on expansive soils. So most of them have problems. A lot of them have problems. So you see this pool in Friendswood in here is a floating pool here. This is the one side of the pool. Here's the other side. It's coming out of the ground. Okay, so these are the pools in expansive soils that are poorly designed. This is a pool in Memorial. There's a 40-foot drop here. They put the pool there without the consideration of the drop. The edge of the pool cracked and dropped. When you put the pools next to slopes, you got to put them on deep foundation. Check for slope stability. This is a pool in Westview. Coming out of the ground. Look at it, about 16 inches. They emptied it over the weekend to clean it up. But we had a rain, the hydrostatic pressure pushed it up. They sued. The insurance company said they're not going to pay anything. It's the owner's fault for removing the water to clean it up without relieving the hydrostatic pressure. So they said it's safe, sanitary, and livable. So you're not getting any money. This is a pool in Cypress Wood area. The hydrostatic pressure just pushed it out of the ground. To build a pool, if your soils are non-expansive, you dig a hole like this, you put your steel in, you put shotcrete in it. If it's dry, you call it gunite, you add water to it at this valve in here. Basically, the way you do pools nowadays, you either go with expansive soils, a structural pool on piers or helical piles with void boxes, remove the expansive soils and replace with non-expansive soils, or use chemical stabilization to put the pool in. The cheapest one is use chemical injection. Affect your trees and foundations. We love trees. Everybody wants to have trees near their houses. But these roots can do things. Tree can fall over your house. Tree roots grow three-dimensionally. Here's my house. The tree's growing right there, right through it. Vacation house. The condo in Florida. The backyard, the tree house. Here's a tree hugger. So everybody wants to have trees around their houses there. But these trees can cause problems. If you dig next to a house with the trees, you may see a lot of roots. Before you build a slab, get all these tree roots out. They basically decay and create voids, and the house can settle. If this is your concrete slab, these are the soils underneath it. And when the tree roots decay, you got these cracks, allows the water to travel and cause heave of the slab. Trees affect foundations in three ways. One way is tree root heave. That means the root itself gets underneath the foundation and start heaving. Just goes out there and start lifting the wall here. You see the sidewalk here just being lifted up. Roots go out there and just tear up that sidewalk. Willow tree going underneath the house there. Here's a root. The inside the house is heaved up. Pine trees, they got horizontal roots too. Goes underneath the house, the bedroom, heaved up. Jackhammer the bedroom. They pull out the root system. Here's jackhammer in another part of the house. You see the root systems. So that was the root heave. Now, if you cut a tree and you build a house on it, the ground heaves up. So if you got a lot in Westview, you cut this oak tree here. And by the way, trees don't know anything about fence line. You cut this tree, this house is going to move up 5 inches in Westview. It doesn't matter, you got a fence here. You got to design this house assuming this tree is going to die someday. Which when it dies, the house is going to heave up. So if these trees here die, or if you cut them, this house here is going to heave up. If your site is wooded prior to construction, and you cut all these trees used to soak moisture out of the ground. The whole ground was dehydrated. You cut the tree, the area is dry, it rains, it starts rehydrating, the ground starts heaving up. So if you got this building here, you got point H and point F. That's where the tree is, next to point H. You cut this tree, the ground is going to heave up, point H. It goes on for about 20, 30 years, rehydration. That's about 6.3 inches. Point F is far away. moves about 20 millimeter, which is almost less than 1 inch. So what the moral of the story is, when you cut a tree, you got to consider that in your design. That's what a lot of geotechs and structural guys fail. They don't consider the effect of trees on their foundation. You cut this tree here next to this building. You see that basically all the branches go all the way up here. That means your root systems go all the way here. The building will heave up when that tree dies. This is how the moisture profile is. If this is your tree here, you got a cone here. This is twice the height of the tree. So if the tree is 50 feet, this is 100 feet distance. Twice the height. This cone of moisture removal to a depth of 10 feet. So this is the tree to a depth of 10 feet. You got moisture deficit, twice the height. Your tree dies or you cut this tree, this whole area is dehydrated, wants to rehydrate and starts heaving up. You got to design for it. The drip line is over here, but the root spread passes the drip line. This house in Austin, they had 3 trees in the backyard. They cut them. They had highly expansive soils. The soil was PI between 50 and 60. 2 large trees were removed. Within 2 weeks, the soil rehydrated and it moved up 8.2 inches. So here it is. A&M doing research. They say it takes about 5 years for a tree, when you take out the tree out, for the soil to rehydrate in general. We've seen it takes more than that. Within 1 year, you got 44% rehydration. Within 5 years, you got 100% rehydration. So you go out there and do custom home, you cut a tree, you want to pull the house on top of it, you better design for it. Otherwise, you're going to be calling me in 5 years telling you have foundation problems. Third concept that affects trees on foundation is shrinkage due to moisture removal of the tree. You got this building in here, you got these post oak trees here. These trees suck the moisture out from underneath this building. You go inside the building, you see the crack right there. So the whole tree, the tree is sucking the moisture out. That building over there had 12-foot piers, which is way too shallow. The whole thing starts going down. This is a slide from University of Texas, distance of a tree from a house. It's a future height of the tree. D over H of 1 is 0.2 feet. That means that tree can cause 2.4 inches of shrinkage at the edge of this house here. So if you got a house here with this tree in here, that tree is going to suck the moisture underneath the slab, and the whole thing is going to drop, create a void underneath your slab. These are different types of trees and how far they should be away from your house. Ideally, you want to put the trees as far as you can from a house, minimum of 20 feet away. Oak tree should be about one of its height. So if it's 50 feet high, you want to put it 50 feet away. Lime tree, 0.5 H. Willow tree, 1 H. Elm tree, 0.5 H. So depending on tree species, it can have effects on your foundation. So this section of the presentation was called Trees from Hell. Some measures to prevent tree distress. You create basically low areas for the moisture to come in and keep the area moisture so the tree roots does not travel too far to get moisture. You put sprinkler system around the tree to keep the tree roots wet. That way they don't have to travel to get moisture and cause structural problems. You plant trees when you plant them with a vertical root barrier system, so the root systems go down as opposed to horizontal. These are root barriers. You can use herbicide root barriers. They last about 10 years. They stun the root systems. They don't penetrate them. But after 10 years, they're no good. So the best thing is to use a thick plastic root barrier system that we specify in our reports. You need a minimum of 20 mil root barriers. Or you put pots around your building or your houses. No planter areas, no trees, just put pots there. Sewer leak, plumbing leak. In the cases where you're on projects, when you got old houses, you got plumbing leak, the floor slab settles, you got a void in here because the soils are so soft because of the leak. You dig a hole out there, you see the whole area is leak and wet and water coming in. You got to go in there and replace all the put new plumbing in. You test the water over there, plumbing test. You do hydrostatic test for sewer lines. You fill the sewer with water for about 30 minutes and watch for it to drop. Video inspection. You do a video system to see if there are any cracks in your storm sewer sanitary line. Water pressure test. Pressurize the water with supply lines with 5 psi above the and hold it for 30 minutes. This is a video test. You run it through the hole in the storm sanitary line or storm sewer through one of the holes. You can see root system is coming through. If you want to know there's water underneath your house or your building, you can do what's called a resistivity test. You put probes in the ground and run electrical current through it. These are the probes. You put in there, this is a medical building. Run current on it. This is the concrete. The red stuff is concrete. The blue is all the water is in there. So you can go ahead and get you got concrete, it's got high resistivity. It shows up as red. Water's got low resistivity, shows up as blue. So you can get sections of your building and show how much water you got everywhere. You can do GPR, ground penetrating radar, to see what's going on underneath your slab. We just did it for another building. The GPR uses an antenna that transmits electromagnetic energy similar to what cell phones use. A receiver is inside. It receives and reflected the signal when it encounters the interface between two materials with contrasting dielectric materials properties. Okay, this is basically a GPR. It hits the pipe. It sends the reflection back in the waves, and it picks it up here. It's a typical GPR there. More GPR. It's Daisy. You run it around the house. You get a diagram like this. Shows where the pipes are. Show where typical voids under the slab are. This is the job we just finished, July 2020. And you can see in here the voids under the slab. These are all voids. And here's all the moisture under the slab. Picks all the moisture areas. There's a lot of void under the slab. You can pick up where the steel is. The steel, like the floor slab with GPR. You run it on there. This is the steel locations. Tells you what the spacing of the steel is. Where the pipes are. Also GPR, you can use it to see if you got compaction of the soil. Here the soil is compacted, 80, 85. Very low compaction. Bad compaction of the soil pad. You can check the concrete. Concrete unit weight is 150. But here is 125 in some areas. That means it's got too much water in the concrete here. So if it cracks or something, we know why. You can also do infrared testing to see if there's a problem on a structure. Here's a under slab leak. You can see the temperature gradient, hot water temperature. With the color, you can see there's hot water here that's leaking here under the sink. Here's the moisture in the carpet. Okay, cold water. The interior water leakage. Here's the hot water leak out here. It's hotter. Here you can look at the buildings and look at for insulation to see if the insulations are there or missing. Here's the missing wall spaces, bat insulation missing. Here's a leak around the light fixture. So you can use infrared to kind of see if there's a kind of a leak anywhere. Geologic faulting, we talk about the fault maps and cause building structures on failures. Drought can cause problems. In 2011, we had drought in Houston area. The whole Texas was on the drought, very, very basically dry, whole Texas. 2018, we had a lot of rain, everything was fine. 2019, we had some drought. 2020, November 20, we got a lot of drought out here in the Panhandle area. Harris County, we don't have any drought. When you had drought out there in 2011, 2012, here's was Lake Houston and here's, Lake Travis. It was empty. It looked really bad. There was no water anywhere. In terms of rainfall in 2011, we had 24 inches for the whole year. Average we have in Houston is about 50 inches. 2018, we had 56 inches. 2019, we had 52 inches. Right now, we have 36 inches. We're down on our rainfall this year. Okay. So when you have a drought situation, the moisture in the soil drops, gets to what's called a wilting point. The trees starts dying. When your soil suction, it drops below 4.5. Soil suction is described as the ability of the unsaturated soil to attract retained water in terms of pressure. It's 4.5 pf, which base 10 of height of centimeters of water column that soil suction would support. Okay, so at soil suction of 4.5, your trees will start dying. If you have a drought situation, foundation performance after a drought, average rainfall in Houston about 50 inches. You go in there about 2008 and build a house, okay, when we have lots of rainfall, okay? And then you get into a drought situation. Rainfall, get into a drought. You get edge drop or swelling at the center. We call it center lift or edge shrinkage. Now, if you install a house when it's a drought and then we get a bunch of rain, we got a drought situation here. We got only 24 inches of rain. All of a sudden, you're going to get a bunch of rain. You got edge heave. It puts the house in compression at the top, tension at the bottom, causing cracking. So you get edge lift. When you evaluate a foundation failure, you look at aerial photos. You see these ditches, they went out there and filled them up. Then they built these houses. 50 of these houses have foundation problem due to settlement and poor compaction. This is Eagle Spring. They went in there and built houses on top of this ravine here. But you can clearly look at it on the area photos. There was a ravine there. So if you have bad compaction, you got to check compaction. We go back when we do soil tests for the builders after the lots are ready and check for compaction. So home builders got to make sure you got compaction for all the field for every single lot. If you don't have it, you got liability. So we go back and check compaction for every lift. Forensic engineering court. Less than 10% of the cases go to trial. Most cases settle after the lawyers make their money. For cases going to trial, forensic engineer plays a major role. When you do forensic engineering, sometimes you have to look at things from different perspectives. For example, Mount Rushmore, this is the front and this is the back. A lot of stuff that we're talking about is in our website, geotecheng.com, publications, guidelines. Please send me pictures of failed buildings, houses, whatever. It makes the presentation interesting. We're going to do a program evaluation. Please look at it and see if you like the presentation. If you have any questions or comments, please let me know. You can call me. You can contact me at email de@geotecheng.com. My number is 713-699-4000. We got one more presentation this year, December 3rd, my birthday. Geotechnical guidelines for design of bridges. Anybody's interested in that? You're going to get your PDH hours from GHBA within the next couple of days. Questions? Questions? It's been quiet, so if you don't have any questions, I appreciate your time. You all have a great day. Please send your information in so that we can put you on the other seminars. Thank you. You all have a great day.